Hey, welcome, guys. Welcome to our final paper one boot camp. How are we doing? Can you guys hear me okay? Let me know in the chat if you can hear me clearly. Hi, Doggy Rocky. Hi, Harman. Hi, Abdul, Dimipu. Good to see you all. Good to see the chat is already popping. How is everyone doing? Yes, you can hear me. Great. Guys, today is chemistry paper one. This is the schedule. I see a lot of names that I recognize from the last few sessions. So biology paper one is done now. Physics paper one is done. We're on to chemistry paper one. This is the third out of 6 sessions that we're doing today. This Easter holiday, sorry. You love chemistry, says Medina. Interesting. That's good to hear. Good to hear. That's something I hear a lot. People find this the hardest. Is that what you guys think, or do you guys find physics the hardest? But that's good to hear. Good to hear. Hi, Mercy. Well done on your wheel spin last time. Good to see you again as well. So, guys, chemistry is surprisingly longer than biology. You'd think that biology has more content, but chemistry has 5 topics in paper one, 5 topics in paper two. So this is the one that's most likely to overrun. So I'm going to try and get started ASAP. Just before I start, just want to remind you guys, if you want to chat, subscribe to the channel. Remember to share this to your friends as well. This is the last free one that we're doing, so try and help out your friends as well. Share the stream. We're going to go through the revision guides that we sent across to you guys when you signed up. So have those in front of you. We're going to basically be annotating those so that you guys have the perfect revision guide at the end, by the time Easter finishes, so you can revise for that final stretch before exams. Exams are next month now, officially next month. So not long left. If the stream goes down, I said this before, it doesn't usually go down. Last time we had a really good stream. It was clear. Just in case it goes blurry or anything, just bear with us. We haven't had to have a stream cancelled before or like go fully down. But if it does, then we'll send you guys an email or something. So keep an eye out on your emails. What else do I need to tell you? I need to also tell you we're going to be following mainly the combined topics, and if you're doing triple, we will extend those sessions. So this is what the timetable looks like. So it'll be 4 sessions. So the first one is 10 to 11 a.m. Then we have a break, and then so on. We have a lunch break as well and another small break. If you're doing triple, especially for this paper, your breaks are going to be shorter because there's that extra content that you guys need to know about. If you're doing foundation, then all you need to do is ignore anything in the spec that says HT only or higher only. Those things aren't relevant for you. Other than that, everyone needs to pretty much know the core content that we're going through today. Is this paper two? This is paper one. Chem is the easiest, except electrolysis. Yeah, electrolysis is by far the hardest topic, in my opinion. We're going to go do that today. What's everyone else saying? What days will bio paper 2, chem and physics be? So next bootcamp is bio paper 2. That's going to be on Tuesday. Chem paper 2 is going to be Thursday. And physics paper 2 is going to be Sunday, just before school starts. Those are the dates. So yeah, sign up to those if you guys are interested. If you like what we've been doing here for the last few days, then there's more of that basically for paper 2s. So get yourself signed up for that. Right, guys, let's get straight into it then. First topic in chemistry is atomic structure and the periodic table. We're going to talk about atoms first. So atoms are things that make up everything in the universe, right? So they make up all matter. They're the smallest part of an element that can exist. That's the definition that's in the spec. And they're made up of subatomic particles, 3 subatomic particles. You only need to know these 3. There are more that you learn in A-level physics, that is. They are protons, neutrons, and electrons. And for those, you need to know the charges and the masses. So protons begin with a P, straight in with a memory trick, telling you that they are positively charged. So they have a charge of +1. Neutrons are neutral. Neutral means they have a charge of 0. And the other one is an electron, which has a charge of -1. You need to know the charge and also the mass. Masses, protons and neutrons are the heaviest. They have equal charge, equal masses of 1. So they have the same mass, much heavier than electrons. Electrons, you can just say, are very small for GCSE. It's fine. You can say 1/2000 as well. That's a bit more accurate. But if you look at the spec point, it says, it literally says very small for electrons. So you can get away with saying that in an exam. So what else do we need to know? We know the masses, we know the charges. We need to know that inside the atom, the central section, the nucleus is what we call it. This is different to the nucleus of a cell. This is a nucleus of an atom. Inside the nucleus of an atom, we have protons and neutrons. And so let me put P plus N there for protons plus neutrons. And then orbiting these nuclei, we have electrons. So they orbit in these electron shells or energy levels. You call them energy levels more in physics, but in chemistry, you can just call them electron shells. So we also need to know the radius of an atom and the radius of a nucleus. These are things that people forget. Please memorize these numbers. All right. So I've seen 1 markers on these usually. So it's not a lot of marks, but it's easy to remember. Radius of an atom is 1 × 10⁻10 meters. And the radius of a nucleus is 1 × 10⁻14 meters. So that makes this 10,000 times smaller. A nucleus is 10,000 times smaller than an atom. Another thing about atoms that you need to know is that they have a neutral charge. They don't have an overall charge. And the reason for that is because they have the same number of protons and electrons, and the charges cancel out. Because remember, protons are positively charged, electrons are negatively charged. So if you have the same number of protons and electrons, you have an equal number of positive and negative. They cancel out. So the overall charge of an atom is always 0. Now, any element can be represented with a chemical symbol. So you have a number on the top, number at the bottom. So you have a bigger number, which is always at the top, and the bottom number is the smaller number. The top number is called the mass number. The bottom number is called the atomic number. Don't get those two mixed up. The mass number tells you the number of protons plus the number of neutrons. Number of protons plus number of neutrons. And the atomic number simply tells you the number of protons. It's sometimes called the proton number as well. But in chemistry, you see it as atomic number. So someone tell me, how do you work out the number of neutrons? Can you let me know in the chat? How do you work out the number of neutrons then? So number of protons, you can just look at the bottom number. And that also tells you the number of electrons, because remember, the number of protons is equal to the number of electrons. The charges need to cancel out. So to work out the number of neutrons, there we go. Everyone's got it. Study Buddy's got it. Philip's got it. Jatham's got it. You take them away. You take the top one away from the bottom one. So number of neutrons equals mass number, take away atomic number. Yes, well done, guys. So here we have 2 examples. Lithium have number of protons as 3, and that means the number of electrons are also 3. Number of neutrons, we subtract the 7 by the 3 to give us 4. Potassium, we got slightly higher numbers. We've got 39 and 19. So protons and electrons are 19, and neutrons are 39 minus 19, which gives us 20. So that's how to work out the number of protons, neutrons, and electrons in any atom. Elements. Definition of an element. It's a substance made up of one type of atom, and you can find them all in the periodic table. Remember, in chemistry exams, you're given a periodic table. You're not given any equations. You need to memorize all the equations in your chemistry exams. Periodic table is very handy as well. What else do we have here? So we've said that yes. So every element has a very specific number of protons. The number of protons in an element tells you, so let me say that again. The number of protons in an atom tells you what element that atom belongs in. So if you have another atom, so let's look at this. Let's say we had another atom which had a mass number of 8 and an atomic number of 3, it would still be lithium because lithium always has 3 protons. Potassium, let's say we had one with 40 as the mass number, but the bottom number is 19, it's still potassium. If you were to change the bottom number to 18, then it would be another element. It would be the element just before potassium. So what I'm trying to say here is that would not be potassium. It will be what's before potassium. Is it argon? Is that right? Someone check on a periodic table if you guys got one. Is it argon? 18 protons. So what I'm basically trying to say is the number of protons in an atom tells you what element that atom is. Okay. Yeah. If anyone's got a periodic table on them, just double check. I know after potassium is calcium. So if it was 21, it would be calcium. Yes, it is. Thank you, Abdul. Right. So what do you call these? What do you call it when you have 2 atoms, same number of protons, but different number of neutrons? What do we call that? There we go. It's the isotopes. Philip, you know the whole periodic table. That's lies. You do not know the whole periodic tables. I don't believe you. That's so hard to remember. I did chemistry in uni and I still didn't need to know the whole periodic table. So that would be amazing if you did. Yes, they're called isotopes. So isotopes, definition of isotopes are atoms with the same number of protons but different number of neutrons. You can define it like that, or you can say they have the same atomic number but a different mass number. So here you can see 3 examples of carbon. They're all carbon because they all have 6 protons. So they're all carbon, but they have different numbers of neutrons, which makes them all 3 different isotopes. Is it optional to know the periodic table in uni? You definitely do not need to know the periodic table in uni. It's always given to you in any exam. Yeah, I did chemical engineering, so there was a lot of chemistry in there. I never needed to memorize the periodic table. Next up, we've got compounds. Compounds are different to mixtures. What's the difference between a mixture and a compound? Can anyone tell me? Both of these are made up of one or more chemicals, one or more elements. What's the main difference between the two then? Mixtures and compounds. There we go. Not chemically combined. So mixtures are not chemically combined. So you have different elements which are not combined chemically. So that means what? What does that mean if they're not chemically combined? What can you do to mixtures that you can't do to compounds? Chemically combined. Mixtures, Coral says, mixtures can be separated physically. Yes, exactly correct. That is what you can do to mixtures. So if you have a mixture, because they're not chemically combined, so let's say you had like sand and salt, they are 2 separate things. You can physically separate them using physical techniques, which I'm going to go through. Can be separated using physical separation techniques. Is it possible to separate a compound then? You can't do these physical separation techniques. So what I'm talking about here is like filtration, evaporation, distillation, all of those. You can't use that for compounds. How do you separate out compounds? Some people say no, some people say yes. You can separate compounds, but you need a chemical process. You guys remember that topic, electrolysis, the one that everyone loves? Electrolysis separates compounds, it splits compounds up, right? Or you can just do a reaction. If you do a reaction, you're breaking up the compounds bonds, right? So no, there's no physical separation techniques, but they can be separated chemically. So here I'm going to say cannot, I'm cheating, I'm copying and pasting, cannot be separated using physical separation techniques. And I'm just going to add to that, it needs chemical techniques. So reactions, basically. Reactions, yes. GCSE study account, you got that. Displacement reactions, yes. Any sort of reaction is basically that. Ruby says she likes the electrolysis topic. That's good to hear. That's good to hear. I don't hear that much. So here are some examples of compounds. I've got a whole table here for you guys to look at. You can practice this. You need to be able to count how many atoms are in each compound. This is for you guys to try at home. But let's quickly look at carbon dioxide. Carbon dioxide is CO2. CO2 means there's one carbon atom and there's two oxygens. Whenever you have a two to the right of an atom, it means you have two of those. So in total, you have three atoms here, one carbon and two oxygens. Let's just look at a trickier one. H2SO4 means you've got two hydrogens, one sulfur, and four oxygens. So in total, that's got 2 plus 1 plus 4, 7 electrons. 7 atoms, not electrons, sorry, what am I saying? Okay, so that's something straightforward that they could ask you. Here we go, we've got the spec points here. So remember, guys, use this as a checklist if you know the points here. If you don't know something, go back and check your notes on that. And you can see here, look what they've got in the spec. Mass of an electron is very small. They don't give you a number, so you don't need to know that. But you do need to know the masses of, not the masses, sorry, the radius of an atom and of a nucleus, and the fact that it's 10,000 times smaller. Right, moving on, relative atomic mass. Do you need to know all of those? You don't need to know all of the stuff in the table. No, those are just examples for you to try. They'll give you something, and from that, you need to figure out how many atoms there are and what type of atoms there are. Yeah, but you don't need to memorize all of them. Is there a way to memorize them? Memorize what? You don't need to memorize all these compounds, guys. You don't need to memorize. These are just examples for you guys to try, okay? I'll tell you what you do need to know. You need to know what methane is. You need to know what carbon dioxide is. If you're triple, you need to know what ammonia is. Water, you need to know. The others you can figure out. You need to know the acids as well. The other ones you can figure out. Yeah? So methane, carbon dioxide, ammonia if you're triple, water, sulfuric acid, nitric acid, and hydrochloric acid. We're going to see that later today anyway. Right, relative atomic mass. So remember I talked to you guys about isotopes, right? And what you'll see is if you look at an element in the periodic table, so let's look at chlorine. Chlorine's a good one because what it's got up there at the top number is not mass number. Loads of people think the top number is the mass number. A lot of the times it is. For GCSEs, it is. But in the periodic table, the top number is not mass number. It's relative atomic mass, which is slightly different. A lot of the times they are the same thing, especially for GCSEs. But what relative atomic mass is basically an average mass of all the isotopes that exist for an element, right? So, for example, chlorine. Chlorine has, if you had a sample of chlorine, let's say you had like a gas canister and had chlorine in it. Inside that canister, there would be 2 isotopes because that's how chlorine exists. It exists as 2 isotopes. One of them is chlorine 35. The other one is chlorine 37. Okay. Note that these are mass numbers because they're individual isotopes. They're mass numbers. The number in the periodic table is not always the mass number. It's relative atomic mass. But usually those two things are the same things. Okay. Now, in this gas canister, with the 2 different types of chlorine in it, there is a split. So there's more of the chlorine 35. We call this chlorine 35. There's 75% of the gas canister contains chlorine 35. 25 of it exists as chlorine 37. So the relative atomic mass is an average of these mass numbers. But when you think average, this is what you guys will be thinking. You guys will be thinking, doesn't that mean you just do 35 plus 37 divided by 2? And that gives you 36. Is that right? No, it's not. That is not the type of average we're talking about here. It's an average taking into account their abundance. What does abundance mean, guys? Does anyone know what abundance means? So let me say this again. Relative atomic mass of an element is calculated as an average mass of all of its isotopes, but it's not like this because you have to take into account the abundance. What is abundance? Yes, Dennis, you got it. Abundance is how common this isotope is. So it's basically these percentages we have, the 35, the 75 and the 25. You have to take that into account. So the calculation isn't just a simple average. This is what we need to do. Instead of adding the mass numbers and dividing it by 2, we're multiplying the mass numbers by their abundance for each isotope. So for chlorine 35 up here, what we're going to do is we're going to get 35 multiplied by 75. That's the abundance. So let me put an arrow here. 35 times by 75 plus 37 times 25. You add those 2 numbers together, add them, and then you divide it by 100, and that will give you 35 if you work it out. Okay, so here we've got the calculation here. This is what I did. 35 times 75 plus 37 times 25 over 100, and that gives you 35.5. You need to be able to do that, but it's very straightforward in an exam, guys. It comes up a lot, and this is what you'd see. You'd see a table, because I've gone through a lot of past exams, and every time, or most of the times, it just looks like this. They give you mass number, they give you abundance in the table, and you just put it into this formula. And you'll see, if you go on our website, flashrevisionlab.com, you'll see loads of examples like this, because it comes up quite a lot. So it'll be 35, 75%, 37, 25. And they'll be like, calculate the relative atomic mass. So you just put it into these equations. Very simple. Just go and practice if you're not sure on how to do this. You just got to do loads and loads. Someone asked, how do you get 25 and 75? That's given to you in the exam. Very easy. They give you the abundance, and they'll give you the mass number either by telling you, or they'll give you like the chemical symbol, and you just need to pick the top number. Yeah. Or if they say chlorine 35, that means the mass number is 35. Chlorine 37, mass number is 37. Okay. For my calculations, if I get my answers right but my working out wasn't clear, would I still get all the marks? Sarah, good question. Loads of people don't know this, but you will. If you get your final mark absolutely correct and you have no working out, you will get your marks. And teachers don't tell you that because they want you to show your working out. It's better to show your working out, because if you don't get that mark, you get 0. But if you show your working out, you get method marks. So if you show your working out and you get the final answer wrong, you'll still get method marks. But if you just write final answer, you're basically risking it. You're gambling. You're gambling on getting it right. So you either get all marks or you get 0. But if you show you're working out, you're more likely to get 1 or 2 if you're wrong. So that's why I always tell people to show you're working out. I mean, it's all in your calculator, so it makes sense. Yes. Okay. Okay. Next. Yeah, we got a few on our website for free. And if you just look at any past paper, chemistry paper 1, these questions always come up. Chemical reactions. So there's very basic stuff. Word equations. You get 2 reactants. It's not always 2, but you have your reactants on the left-hand side. You've got products on the right-hand side. So these are the 2 things which are reacting together, methane and oxygen, and they're producing water and carbon dioxide. We saw this on Tuesday with photosynthesis, the reaction for photosynthesis. That's a word equation. A symbol equation, you do the same thing, but you write symbols instead. So methane is CH4, oxygen is O2, H2O, and CO2. Now, the thing with symbol equations, you have to balance them. If they're not balanced, they're wrong. So you need to be able to balance them. So let's look at this one. For example, here we can see how many of each atoms there are on the reactant side and the product side. So the goal for balancing an equation is to have the same number of atoms on the left and on the right. So if you have just C on the left, that means you have 1 carbon on the left. We have 1 carbon on the right. If we look at hydrogen, we've got 4 hydrogens on the left because it's H4. We've got 2 hydrogens on the right. And if we look at oxygen, we've got 2 oxygens on the left. We have 1 plus 2 on the right. We have 3 oxygens on the right. So that tells us carbon is balanced. Hydrogen and oxygen are not balanced. We need to balance them. How do we balance them? We add numbers in front. These are called coefficients, but you need to write the right coefficient in front of whatever substance it is. So in order to balance this, let's say first we want to balance the hydrogens because we've got 4 on the left and 2 on the right. We want to make this a 4, right? How can we make this a 4? What coefficient can we add here? We can add a 2 here. Let's add a 2 here. If we add a 2 here, it multiplies everything in there by 2. So it's 2 times 2 hydrogens, which is 4. But what that does to the oxygens, it also means there's 2 oxygens here and 2 oxygens here. So this changes this to 4 now. So let me say that again. Remember, you're multiplying everything by 2. So that makes the hydrogens 4, but it also makes the oxygens 2. There's 2 lots of oxygens here. And then there's another 2 here. So in total, there's 4 oxygens. We want to balance the oxygens now because the hydrogens are now balanced. So last thing to do is balance the oxygens. What we can do here is put a 2 in front of the O2. That's going to make this 4. Now we have 4 and 4 on the left and on the right. So the whole thing is balanced. That's how the final equation should look like. Okay. It comes with practice, guys. It comes with practice. Balancing. Yes. Well done. I'm seeing the correct things here. If you change the small numbers, do not change the small numbers ever. That would be wrong. Never change these small numbers. You're basically changing the compound. All you can do is add numbers in front of the whole compounds or elements. If you're talking about coefficients, you multiply everything by that number. Yeah, that's right, Doggy Rocky. Exactly right. Cool. Moving on. Separating mixtures. Remember, I told you, mixtures can be separated. Here's a difference between mixtures and compounds. Physically combined, chemically combined for compounds. There are 6 different separation techniques you need to know about. So this is separating mixtures, not compounds. We have filtration, evaporation, crystallization, simple distillation, fractional distillation, chromatography. These 2 are more likely to come up in paper 2. Okay? More likely to come up in paper 2. But the other 4 are more likely to come up in paper 1. Just because we learn fractional distillation in organic chemistry and chromatography is like a required practical in paper 2. So I don't think I've ever seen it come up in paper 1. Filtration. It's a straightforward process. It just involves you using filter paper. So you got filter paper here. You put your mixture in. So let's say it has to be an insoluble solid and a liquid. So salt. No, salt is not a good idea. Sand and water. If you had a mixture of sand and water, you can put that in there. And what will happen is the water will flow through to form the bottom, which we call the filtrate. And the sand will remain here. We call that the residue. Filtration. Then we've got evaporation and crystallization. Two of them I'm going to teach you together because they're very similar. So you start off by pouring your solution into an evaporating dish. So these are used for soluble solids dissolved in liquids. So filtration is for insoluble solids like sand and water. This is more for like salt and water. Because salt dissolves in water, you would use evaporation and crystallization to separate them. So you pour them in an evaporating dish and then you heat them. So that's the same for both crystallization and evaporation. For evaporation, you literally keep heating it, keep heating until all the water evaporates. And then you end up with solid salt. Okay, that's evaporation. Very straightforward. Crystallization is slightly different because you sometimes have crystals which will break down if you heat them too much. So you can't use evaporation. If you can't use evaporation, you need to use crystallization. So crystallization, yes, you still put it in an evaporating dish. You heat it, but you only heat it for a little while. You heat it until crystals start to form. Once the crystals start to form, you take it off the heat and you allow it to cool because that causes crystals to form higher, crystals to form more because the solution is more concentrated. So what you have is basically this liquid with crystals forming in it, and you want to take the crystals out. So what you do after that is you filter the crystals out and dry them. So slightly different for crystallization. They're similar, but slightly different. You could gently heat it with a water bath. Yes, you can. If you want to ever control temperature accurately, you can use a water bath. You can use a water bath, yeah. Someone's in school and watching this, okay? I hope you don't get in trouble. Is crystallization required practical? No, none of these are required practicals. First required practical is actually in topic 2. Is it topic? It might even be topic 4, actually. It doesn't come for a while. We're not going to see any required practicals this topic or the next topic, I think. How do you ensure all the water is evaporated? It'll be dry. If it's dry, all the water is evaporated. How do you know when the small 2 is written in equations? Like when they make chemicals, sometimes they remove them. If they change the small 2, that's part of the reaction. You yourself, when you're balancing, should never change the small 2. If it changes in the reaction, that means the reaction's happened and it's formed a new compound. That's why the small 2 might change into like a 3 or it might disappear. But you should never change the small numbers in a chemical equation when you're balancing it. Yeah, study buddy, that is a required practical that comes up later. Oh, someone asked, is crystallization a required practical? I think you're getting confused with the making salts practical. That is basically crystallization. Yeah. So we're going to see that later. So it's not crystallization in separation techniques, it's the making salts practical. We'll see that in the 3rd or 4th session. That is a required practical. Why would you need evaporation? Evaporation is just faster. Crystallization you use if the crystal you're forming is going to break down when you heat it. Some crystals, they break down when you heat it. They just get destroyed. So you can use crystallization for that. Okay. Most common 6 marker in paper 1. I couldn't tell you. There's all sorts. There's not one common one. I'd say required practical ones are more common. Yeah. Evaporating dish is the same as a crucible, Jatana. Yep, that's correct. All right, next we got simple distillation. Distillation is when you've got two liquids with different boiling points. So let's say we had ethanol and water. So ignore the methanol for now. Let's say we had ethanol and water. They have two different boiling points. Ethanol has 72 degrees boiling point. So that means if you heat ethanol up to 72 degrees, it's going to turn into a gas. Water has a boiling point of 100 degrees. You need to memorize that one. Not the ethanol, just water. If you heat that up to 100 degrees, it will turn into steam, right? So what you do is you have your setup here. So you put your mixture of ethanol and water in a boiling flask. You heat it up, but you only heat it up to 72 degrees. Because at 72 degrees, only the ethanol will turn into gas. So the ethanol will turn into gas. The water will remain here because it still hasn't turned into gas. It hasn't reached 100 degrees. Ethanol moves up and it goes down this tube here. This is connected to a condenser. So this is a condenser. It basically cools the tube in the middle. It has water flowing through it. So that cools the ethanol. It condenses it to liquid and the ethanol flows down and you collect pure ethanol here. And what you're left with is pure water here. That's simple distillation. Fractional distillation, slightly different to the fractional distillation that you see in paper 2. You just use a bigger column, okay? Because you're dealing with more than two different compounds. So let's say we had methanol, ethanol, and water. You do the same thing, guys. You'll get the setup, you'll heat it up to the lowest boiling point first, but this time is 65 degrees. So you let that heat up, the methanol will go up, and it will cool down, and the methanol will be collected here. Once you've collected all the methanol, remember the ethanol and water still remains in the boiling flask because they haven't boiled yet at 65 degrees C. Once you've collected the ethanol, you remove your beaker and then put a new beaker in. Then you crank up the heat to 72 degrees. Then the ethanol is going to get removed. And you can keep repeating that. If you had like 5 different things to separate, you can just keep repeating that over and over again. So you just keep putting the temperature up to the next boiling point over and over again. So fractional distillation is basically simple distillation, just repeated. It's different to the one you learn in organic chemistry. So like I said, this is more likely to come in organic chemistry. These little beads here are just to increase the efficiency of separation. There, they don't really ask you on that. What does it do? Yeah, exactly. So the beads just increase the efficiency of the separation. Yes, exactly. Wouldn't the liquids mix in the condenser? No, because remember, you're heating them up one at a time. So only methanol evaporates first because you're heating up to 65 degrees. So you're only going to get methanol up here. So methanol is only going to be here. So methanol is only going to be produced here. The ethanol and water will not have evaporated. So it's just going to stay as liquid down here. Okay. Paper 2, yes. Cracking is in paper 2. That's organic chemistry. Then finally, we got chromatography. I'm not going to go through this because it barely comes up in paper 1. So I'll just quickly recap it. You just put chromatography paper into a solvent like water. The water rises up. You have an ink spot. That's usually what you're trying to separate. That's your mixture you're trying to separate. The water rises up and takes the ink spot with it, and it leaves behind the different components. It separates out into different components, and then that's you separating out the ink into different dyes. You don't need to know about analysis. That's all paper 2 stuff. All right. So chromatography, I've never seen come up in paper 1. Maybe it's a 1 marker asking how to separate the dyes in an ink, and you'll just say chromatography. Which one is stationary and mobile? That's paper 2. Stationary phase and mobile phase, that's all paper 2. So you don't need to worry about that for paper 1. We'll go through that next week, next Thursday. Development of the model of the atom. If you guys were here for physics, this is a topic which is common for physics and chemistry. And I've got this picture here. What do you think that is? Anyone who knows my memory tricks or who was here on for physics on Sunday would know what that is. There we go. We've got DJ red blood cell. DJ red blood cell. Why do we have a red blood cell that's a DJ? Because it helps you to remember the history of an atom. DJRBC is what we're going to use to memorize all the scientists that came up with models for an atom. Okay, so we know what an atom is now. I've already described it to you. It's a nucleus, it's got electrons on its outside orbiting it, right? But we didn't always know that. This model of an atom throughout history has changed throughout. So the first scientists that you need to know about, there are more scientists in this, by the way, but I'm just teaching you the ones you need to know for GCSE. John Dalton. So D is for Dalton. So Dalton basically came up with a very simple model. He literally said atoms are spheres. Very straightforward. He said different elements were made up of different spheres. Okay. Then came J.J. Thomson. J.J. Thomson, who discovered electrons. He discovered electrons. So these negative charged particles. He said these atoms also had negatively charged particles in it. But we knew that atoms were neutral. So he said, okay, so we have negative charges in the atom, but we need to balance that out. So I'll say that the sphere that these negative charges are in is positive. So that's when he came up with the plum pudding model. So the plum pudding model is a sphere of positive charge with electrons embedded within it, like plums in a plum pudding. I've never had a plum pudding myself, but apparently that's what it looks like. Democritus, you don't need to know for AQA. You don't need to know about Democritus. I think that's either Edexo or OCR. But yeah, he was an ancient Greek philosopher who came up with the idea of atoms as well. Yeah, okay, someone's confirmed it. In Edexo, you need to know. Write what they did next to their name. Okay, let's do that. Let's do that. Good idea. So Dalton came up with the fact that it was a sphere. So elements for spheres. God, my handwriting's all over the place today. J.J. Thomson came up with the plum pudding. He discovered electrons. And he came up with a plum pudding model. Dalton's model didn't have a name. It's just called Dalton's model. Then came the big one. This is the one you need to know the most amount of detail because you need to know the experiment for this one as well. You don't need to know the experiments for any of the other ones. This is Rutherford, Ernest Rutherford. He discovered the nucleus because he carried out an experiment. What's that experiment called, guys? Anyone know? Alpha particle scattering experiment. Yes, we got it there. So what he did, he got a thin gold foil made up of gold atoms. Okay. And he fired alpha particles at them. Alpha particles are positively charged. They're made up of 2 protons and 2 neutrons. Okay. And he fired them at the thin gold foil. And what he expected, because everyone believed the plum pudding model back then, he expected these alpha particles to basically bounce back or to be absorbed, to stop, basically. He expected it to not go past this gold foil because it's a solid. So it should just hit the solid and that's it. It should be done. But what he saw shocked him. These alpha particles started going straight through, like 99% of them just passed straight through, no deflection whatsoever. And that shocked him. He made a conclusion from that. He said, right, seeing as these alpha particles are going straight through, and 99% of them are going straight through, pretty much all of them are going straight through, that tells me that most of the atom is made up of empty space. If you look at an atom, pretty much all of it is empty space. And the other observation he saw was that the other 1%, they did get deflected by tiny amounts. Some of them got deflected loads. And that told him that there is mass in the atom, but all the mass is concentrated in a really, really small place. And he called that the nucleus. And he said the nucleus was concentrated in mass and it was positively charged. And it was so small that only 1% of the alpha particles got deflected by them. So those are two observations that he made, and it led to the nuclear model, where he basically said an atom has a nucleus in the middle, and all the electrons that J.J. Thomson discovered, they just orbit around the nucleus randomly. Yeah. No electron shells. He didn't discover electron shells. That's later. But he basically said nucleus positively charged. He didn't know what protons were. And they had just electrons just randomly going round and round and round. Okay. Yep. Well done. Well done. Do you have to talk about protons that were attracted to electron shells? Attracted, they are attracted, but that's not something that he discovered. Why did he use gold? It was easy to get it into a really thin gold foil because he basically needed something which was 1 atom thick, and gold was very easy to like shape. That's why I used gold. But you don't need to know that. What's an alpha particle? Alpha particle is made up of 2 protons and 2 neutrons. It's just a positively charged particle. We're actually going to see that later today, yeah, when we do radiation, radioactivity. Gold is very soft. Yes, good. Then came Niels Bohr. Niels Bohr, who discovered electron shells. And his model, he basically said electrons don't just orbit around randomly. They go around in electron shells at fixed distances from the nucleus. At that point, we also had protons that were discovered as well. So now we have protons, we have electrons. We're very close to what we know an atom is now, right? So what's missing here? What's missing here? What needs to be discovered by the last person? Chadwick. What did Chadwick discover? Yep. Well done, guys. Discovered neutrons. Okay, that's the last one that was discovered. Because they're neutral, it's quite hard to detect them. And then we came up with the model that we use now. That's what you learn in chemistry. All right, that's the model of the atom, the history of the atom anyway. And there you can see common content with physics. I'm pretty sure all of these points are exactly the same as the physics one. And it says you don't need to know experimental work except for the alpha particle scattering experiment. All right, next we've got electron structure. Guys, when you draw electron structures, you have the nucleus in the middle, you have electron shells around them. You need to know up to 3 electron shells. You need to know how many electrons each shell can hold. First shell can hold 2 electrons, second shell can hold 8 electrons, and third shell can also hold 8 electrons. So when you're trying to figure out the electron configuration, the structure of an atom, you fill it in from the middle first, and then you go outwards. So for example, we've got chlorine here. So if we did chlorine, we've got the nucleus here. How many electrons does chlorine have? I think the bottom number was 17 electrons, right? So 17 electrons. You have to put that in the form of 288. So you fill in the first electron shell first. 1, 2. Now that shell is full. We've used up 2 electrons from our 17. We have 15 electrons left. So we go into the second shell. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons that can be filled in the second shell. That is now full. So we've used 8. We have 7 more electrons to fill because we've used 8 from our 15 now. So we go on to our third shell. And you start filling in your 7 and 2. Oh, you guys can't see that. 1, 2, 3, 6. And then I'll put the 7th one up here in a different color. So that's 7 electrons there. Let me move it down so it's a bit clearer for you guys to see. Seven electrons. Yes. So the electron configuration is 2, 8, and 7. Jada, you don't need to write 18. That's more of an A-level thing. I don't know if you did that on purpose or you accidentally typed that in. You only need to know 288. If you have anything past 288, you just add it on. So like calcium, for example, you have 2882. And you should never get asked any elements past calcium. Calcium is the biggest electron configuration that you need to know. And that's 2882. Okay, past that, it's complicated. It's A-level stuff. They won't ask you that. All halogens have 7 electrons in the outer shell. Yes, we're going to go through halogens in a second as well. So yeah. Right, next, we need to know about the periodic table. Wow, 50 minutes gone already. Periodic table. You need to know the history of the periodic table, and you need to know about the modern periodic table as well. So, early periodic tables. People had, just like the structure of the structure of the atom, the model of the atom, there was always models that we've developed. The periodic table as well. We've developed several different models of the periodic table. At the very beginning, we didn't order elements in order of atomic number. So right now in the periodic table, if you look at the periodic table, you'll see that all the elements are in order of atomic number. You start off with hydrogen, which is 1, then helium, which is 2, lithium, which is 3, and so on. But back in the day, we didn't know what atomic mass was because we didn't know what protons, neutrons, and electrons were. So what we used was something else, atomic weight, which was literally the mass, okay? And it was worked out by scientists. You don't need to know how, but they used the physical atomic weight instead, not atomic mass. Because it was the only measurable data that early scientists could use. Now, when they put these elements in order of atomic weight, they realized something. They realized that properties kept repeating over and over again, periodically. That's why we started calling it a periodic table. So here you can see you have the colors. Let's say the colors represent the properties. The properties kept repeating in the same order. Now, loads of scientists just try to force all the elements that had been discovered at that time in a periodic table with no gaps. But this was an issue because if you do that, the properties would not fit properly. All right. So for example, this element here was not discovered. Okay. So loads of people just, let's see if I can do this. Yeah. So loads of people would have just pushed titanium here in this position, vanadium here, chromium here, magnesium here, manganese here, and iron here. Yeah, imagine getting these 4 and shifting them all to the left because this element had not been discovered. Okay. So there was a scientist, Dmitry Mendeleev, who basically did something different that all the other scientists didn't do. He recognized these patterns and he didn't force elements into groups they didn't belong in. So all the other scientists would have put titanium here, even though it had the same properties as carbon and silicon. And that just messed up the whole periodic table. He recognized that there were some elements like this that had not been discovered. So what he did was he left gaps there. He didn't put any elements there. And his periodic table had loads of different gaps in it. And he made predictions. He said, right, there's a gap here, but I bet you we're going to discover this element one day, and it's going to have this property, this property, and this property. And he said that. And then a few years went by, and people discovered the element. So he called this one, for example, Eka aluminium. And years later, people discovered it and all of his predictions were right. So people started using his periodic table because it was more accurate. So how does Dimitri know elements had been discovered or not? So he didn't know, he figured it out because he just looked at all the elements and he saw that they all fit in these patterns. And then he said, okay, there's this one with this weight, there's aluminium with this weight. There should be one more which has a weight of around 43, but we don't know what it is. So he basically said, no, we haven't discovered this element. We need to discover this element. I'm going to leave a gap here. You guys can fill this in a few years' time. And that is what led to our final. This was the biggest change that we had in the periodic table, and it was the most important one because he left gaps, predicted them, and the predictions turned out to be right. And also, he changed the orders of some of them. So there's like an example. I think it was iodine and tellurium. Iodine and tellurium. So two elements where one element had a higher mass number than the other, but he switched their order so that the higher one was before the lower one. And he switched them because they fit the pattern better, the properties better. So he didn't care that one had a bigger atomic weight. He just switched them anyway. He said, nope, this one definitely belongs to this group because it has the same properties. And it turned out to be the right thing to do because atomic weight is not the best thing to order elements by. Atomic number is better because now we know what protons, neutrons, and electrons are. Atomic number works much better. And if you do order them in order of atomic number, the order that he proposed was correct. And we only knew that because we knew what isotopes were. It was the isotopes that were causing the atomic weight to be different for iodine and tellurium. So the discovery of isotopes basically agreed with what he was saying. Okay, is Dmitry Mendeleev alive? Nope. He's long gone. Did it come in a dream? You don't need to know that. I don't know if it came in a dream. No. Okay, so now we have the periodic table we deal with now, which is everything in order of atomic number or proton number. We have discovered all the elements up to a certain amount. I think you guys just need to know about 118. You guys get a smaller periodic table than the real one. Metals are on the left, metals here. Non-metals are on the right, and they're split by this staircase. You don't get this staircase in your periodic table, guys, so make sure you know how to draw this. Yeah, so you go down to boron, and then just go left, right, left, right, left, right, left, right. So split the boron and the aluminium. So maybe like at the start of an exam, just go straight to your periodic table and split it up. So just so that you know. The vertical columns are known as groups. So we've got group 1, group 2, and so on. And the horizontal rows are called periods. And what you have is elements in the same group have the same properties because they have the same number of electrons in the outer shell. So from the group numbers, you can tell how many electrons an atom has in its outer shell. So for example, group 6 has 6 electrons on its outer shell. All of these elements have 6 electrons on the outer shell. Okay. What do we have here? Metals and non-metals. So I've just talked about metals and non-metals. The further left you go for metals, the more reactive they are. So group 1 is the most reactive, and we're going to talk about that. For non-metals, the further right you go, the more reactive they are. But I'm going to talk about that when we talk about group 1 and group 7. I'll talk about that. All of this stuff I'm going to talk about when we go through group 1 and then group 7. So don't worry about me skipping this. Okay, let's have a break. It's 1 hour. We need to go through group 0, group 1, and group 7. We'll do that in about 15 minutes. Triple guys, just stay with me. We're going to quickly go through transition metals. That would take about less than 5 minutes, I think. Not even that. 3 minutes. Transition metals. Very quick. We'll be back at 11:15 combined, guys. I'll see you in 15 minutes. Triple guys, stay behind. Why did I pick triple? You picked triple. I thought your schools assign you triple. Let's go all the way to the end here. Look, very straightforward. Look at this. It's one page. It's one page. Transition metals. So you need to know where transition metals are. It's in the middle of the periodic table. Yeah, it's that little middle block that we have here. What are transition metals? How are they different? They can form more than one type of ion. So like copper, for example, you can get Cu2 plus ions and you can get Cu plus ions. Yeah. They're often colored when they make compounds. So copper sulfate, for example, is a bright blue color. That's the second thing, the second property. And they're often used as catalysts. We're going to talk about catalysts later. Catalysts speed up reactions without getting used up. You need to be able to compare transition metals with group 1 elements. So we're going to go through group 1 elements straight after the break when we go through alkali metals. Main thing is transition metals have higher melting points, higher density, so they're generally heavier, they're stronger, they're harder as well. In terms of reaction, group 1 elements, and we're going to explain why, they're much more reactive. Group 1 elements are much more reactive than transition metals. Okay, and that is literally all you need to know for transition metals. You don't get asked much at all. Okay, so yeah, triple gang, that was it. That was it. We have more triple stuff to do. We have a lot more to do. We've got to do titrations and more calculation stuff, but we'll save that for after. So be prepared to have a much shorter lunch, guys, unfortunately. But I am trying to get through the whole chemistry syllabus. So yeah, unlucky, guys. Okay, let's have a break. I'll see you back at 11:15. Yes, yes. Back to chemistry it is. I see people talking about English. Is that English? I'm not sure. I see some quotes. Right, guys, before we get started, just to remind you guys, we've got our cram classes coming up. These are going to be the day before each of your exams. So we have one for each paper in science. So that's 6 days. You guys can sign up for free. All the paper ones are free. And we're going to do another spin the wheel where one of you guys will get access to all of the cram classes and all the paper twos next week as well. If you've already signed up to them, don't worry, we've got your names. We're going to include it in the wheel. If you haven't, then join the link that I'm sending here and sign up on that. It takes like 2 seconds to do. Is there a deadline to book paper two? Not really, not really. Whenever you get the chance, you can book it then. Yeah, I just wanted to say that before we start. So we'll spin a wheel, and one of you guys will get access to all the paper twos and the cram classes as well. Right. We're going to look at group 1 and group 7. Right, so group 1 elements. They have 1 electron on their outer shell. Okay, so I'm going to show you a memory trick in a second. Before that, let's just quickly go through group 0. So group 0 elements are known as the noble gases. They're noble because they're not reactive. They're kind. That's why they call them the noble gases. They're not reactive because they have 4 outer shells. All of them have 4 outer shells, meaning their structures are stable. Okay, we're going to talk about that quite a lot in the next topic, which is bonding. Now, they are monatomic atoms. We're going to look at halogens. Those are diatomic molecules. Monatomic means they exist as single atoms. Diatomic, for group 7, they exist as 2 atoms in a molecule. Other things you need to know about noble gases, there's not much, but as you go down the group, the boiling point of these gases increase. Reason why is because intermolecular forces between the molecules get stronger. We're going to talk about intermolecular forces again in bonding, but for now, yeah, the boiling point increases because the intermolecular forces get stronger. Other things you need to know are the fact that they're non-flammable. They don't ignite like other elements do, again, because they're very stable and they don't react. So they have 4 outer shells. On to group 1. So group 1 metals, the alkali metals, they have 1 electron on the outer shell. So you can see here we've got lithium, sodium, and potassium. They all have 1 electron on the outer shell. As you go down the group, they get more reactive. And you need to understand why. So when these react, when lithium reacts, when sodium reacts, when potassium react, all of them, what they want to do is they want to achieve a full outer shell because right now they're not very stable. They're not like the noble gases. In order to become stable, they need to lose these outer electrons. And as you go further down the group, it gets easier to do. Reason why is because think about what's holding these electrons together. The nucleus is positive, right? Electrons are negative. So they're attracted to each other. So it's that positive nucleus that's holding the electrons in place. They're orbiting around, but they're being held in place. Now, for you to remove that electron, when you're reacting it, you need more energy to remove an electron that's closer to the nucleus than one that's further away. So sodium is larger than lithium. That means its outer electron is further from the nucleus. So think about magnets. If you have magnets which are further away, they're less likely to attract. They attract less, right? It's the same here. The lithium one is closer. The lithium electron is closer to the lithium nucleus, so there's more attraction here. So you need a lot of energy to remove that. But for sodium, because it's further away, there's not much attraction. So you don't need as much energy to take that away, to take that electron away, meaning the reaction is much more vigorous. So as you go down group 2, reactivity increases. We're going to jump to group 7 and we're going to compare this to group 7 because for group 7, it's the opposite. As you go down group 7, the element gets less reactive. Why is that? That's because in group 7, you have 7 electrons on the outer shell. You're not trying to lose electrons here. These are non-metals. You're trying to gain electrons. It's trying to pull an electron to its outer shell because that's the easiest way that it can get a full outer shell and become stable. If we compare chlorine, which is bigger, to fluorine, which is smaller, it's easier to gain the electron with fluorine because, again, there's more attraction. More attraction, they're closer together. It can pull that electron down much more easily. So that means this can react very easily because it can gain electrons easily. Whereas chlorine, because the electron's further away, it's going to need more energy in order to attach onto the outer shell to make it full. So what we need to say here is that as you go down group 1, they get more reactive as they go down. So what we can do here is we can get that 1. If you draw a 1 like this, not a straight line, and imagine reflecting it. If you reflect that 1, you get an M to remind you that it gets more reactive as you go down the group. For group 7, get the 7 and flip it upside down. Rotate it to get an L. That tells you that it gets less reactive as you go down the group. So that means fluorine is the most reactive halogen. Another thing you can use here to help you memorize things is alkali metals. The reason why they get more reactive is because they need to lose electrons. So they lose electrons in order to get a full outer shell. Whereas halogens, group 7 elements, that's what they're known as, they need to gain electrons. Just a way for you guys to remember that. So you need to know these trends. What else do you need to know about group 1? Let me tell you. You need to know some reactions. So group 1 elements, as you go down the group, we've already explained the reactivity increases. They get more reactive. They have lower melting and boiling points as you go down, so they're easier to melt. And in terms of their reaction, they react with water very vigorously. So lithium, sodium, they both land on water, they melt into a ball, they float around the surface of the water, and then they pop. A lot of bubbles are being produced. That's because hydrogen is being produced. So lithium plus water forms lithium oxide plus hydrogen. You need to memorize these. And you need to be able to write this type of equation for any group 1 element. So here it would just be Li, 2Li, and LiOH. You just replace the X with an alkali metal. The further down you go, the more violent it goes. And you can see that from this table here. Lithium, these are the observations, is what I just said. But for potassium, there's something extra that happens that you need to remember. If potassium reacts with water, the potassium melts into a ball, but also ignites with a lilac flame, a purple flame. It floats around and then it pops. So as it floats around, it also produces a lot of bubbles, and that's the hydrogen bubbles that we're talking about here. Okay. Next up, we have got reaction with chlorine. So when you get a group 1 element and you react it with chlorine, you get a metal chloride formed. So you need to be able to do that with any type of group 1 element. Again, just replace the X with a group 1 element. So that could be potassium. If you replaced it with sodium, it would look like this. So 2Na plus Cl2 goes to form 2NaCl. Sodium plus chlorine forms sodium chloride. All of these are white salts. It's white salts that get formed. And then the final one that you need to know is the reaction with oxygen. If you get a group 1 element and you react it with oxygen, you get a metal oxide form. So lithium plus oxygen forms lithium oxide. So I've given you all the general equations here. You just need to memorize them and be able to write them for any group 1 element. Okay. Yes, combine needs to do what we're doing currently. Yes, and triple need to do what we're doing currently as well. Group 7, so I've told you already about the reactivity of group 7, the halogens. The other thing I mentioned earlier, remember that group 7s are diatomic, okay? They exist as 2 elements, so Cl2, F2, Br2, I2. Trends, you need to know a bit more about halogens. You need to know how they look like, okay? So fluorine is yellow. As you go down, the color gets darker. So you can see chlorine is green-yellow, then bromine is red-brown, and then iodine is dark gray. Their state changes as well. Fluorine and chlorine are both gases. Bromine is liquid and iodine is solid. And unfortunately, if you're AQA, you also need to know the color in solution. So that means if you were to get chlorine and put it in water, you need to know what color it's going to form. It's going to be colorless. That's why swimming pool water is colorless. It's like normal water. When you dissolve chlorine into it, it turns colorless. Bromine will turn orange. And you can remember that because in paper 2, you learn about bromine water. And you use that to test for alkenes, right? It's orange at the start. Iodine, you can think about biology. Biology, you use iodine solution. Iodine solution is not dark gray. It's brown, isn't it? It goes brown to blue, black. So iodine dissolved in water is actually brown. It's a different color. How can you memorize the equations? You can't really memorize them, to be honest. You just need to go through them, basically. How do I know if a compound is solid or aqueous? If it's dissolved in water, it's aqueous. Yes, the AQA have to know the colors in solution as well as their normal color. So these are their normal colors. And then you also need to know their colors in solution as well. Yeah. So trends you need to know. As you go down the group, I've already explained this one. Reactivity decreases. Boiling point increases. You need to explain that. It's the same as the explanation for the noble gases. Remember I said, as you go down the group, the noble gases have a higher boiling point. Same with these gases as well. The reason why is because they have stronger intermolecular forces, which require more energy to break the bonds. The color always also gets darker. You don't need to explain why, you just need to know that. And I've explained this already. Now, reactions that you need to know. You need to know what happens when you get a group 7 element and react with hydrogen. It just forms a hydrogen halide. So hydrogen and chlorine will form hydrogen chloride. Hydrogen and fluorine will be hydrogen fluoride, hydrogen bromide, hydrogen iodide, and so on. This is the symbol equation of an example. You could react them with a group 1 element. So we've seen this equation already for group 1. It might be potassium. Let's say we had potassium here. Potassium plus chlorine would form potassium chloride. These are all things you can figure out in the exam. You just need to think about the names. You need to make sure you write the names correctly. The one that gets asked the most is displacement reactions. So a displacement reaction is when a more reactive element replaces a less reactive element in a compound. So look at this. We've got potassium bromide reacting with chlorine. Chlorine is more reactive than bromine. I told you already, because it's higher up, it's more reactive. The reactivity decreases in group 7 as you go down. So chlorine is more reactive than bromine. That means the chlorine is basically going to swap with the bromine in potassium bromide. And what you're going to get formed is potassium chloride instead, and bromine is going to be released after. Okay. but it only works if it's more reactive. So look at this example here. Potassium chloride reacting with bromine would not work because bromine is less reactive than chlorine, so it will not displace the chlorine. So this would not react at all. You wouldn't get a reaction here because it's less reactive. So this here is a table of the summary of all the reactions that you need to know. And it's basically just 3. But this doesn't have to be potassium. It might be sodium chloride. So as you can see, they can only react if they're reacting with an element that's more reactive than the one in the compound. There is a lot of info, I know, I'm sorry. But the good thing is you can rewind back. So I'm trying to find the balance between getting everything done and trying to explain it as slowly as possible. But this is topic 1. We've got 5 topics to go and we're already on part 2. So I'm trying to get everything covered as well. This is the thing with chemistry, unfortunately. So yeah, that is topic 1 done. Okay. Topic 2 is bonding. Huge topic here. So 3 types of bonding you need to know: ionic, covalent, and metallic. And I'm going to go through the first 2 at the same time. All right. So ionic and covalent. I'm going to talk to you about the difference between them. So covalent bonding involves the what? Can anyone tell me in the chat what it means? And you can use the word companion to kind of remind you what it means. Companion means friends. What do friends do? Friends like to share. Exactly. So this involves the sharing of electrons. So covalent starts with CO, companion starts with CO, friends like to share. This involves the sharing of electrons. The other thing you can get from this is in companion, you get NON, which is non. That reminds you that covalent bonding happens between non-metals. It only occurs between non-metals. The other thing you can see in covalent, if you look at the green letters, you've got V, E, and N. Venn. What's that? Do you guys know what a Venn diagram is in maths? Hopefully you guys know what a Venn diagram is. A Venn diagram is when you have circles overlapping. So this reminds you that the diagrams for this look like a Venn diagram. Okay. So 3 things that we're going to learn here when we do covalent bonding. Ionic bonding, what you can do to remind you the differences between covalent and ionic is you can get these 2 I's. You can put them together to make a positive sign, and you can get 1 and rotate it to get a negative sign. So that's a plus and a minus. So this gets formed by positive and negative atoms. What do you call atoms which have a positive and negative charge? What do you call these? We call these oppositely charged ions. Yep. Well done, guys. Well done. So that reminds you that ionic bonding occurs between oppositely charged ions. And also, because they're opposites, what else are opposites? They occur between metals and non-metals. All right, so let's go through these in a bit more detail. Let's start off with ionic bonding, what I just explained. So first of all, let's understand what ions are. If you get an atom and you remove an electron from it, it turns into an ion. If you add an electron to it, it turns into an ion. But they turn into different types of ions. All right. If you lose an electron, if an atom loses an electron, it becomes a positive ion. A positive ion is also known as a cation. If something gains electrons, you're basically adding more negative charge to it, right? So that means it turns into a negative ion. We call those anions. We talked about metals and non-metals earlier. Metals form positive ions, non-metals form negative ions. So if we looked at sodium, for example, sodium isn't very stable right now because remember, it doesn't have a full outer shell. In order to give it a full outer shell, we need to remove this outer electron. We need to lose that electron. You're taking away something negative from it. If you take away something negative from it, it will become positive. So you show it as an ion. So look here, I've just removed that outer electron now, right? So I've only got the two shells here, the first two shells here. And I've shown it's positive by putting square brackets around it and putting a positive charge there. That's how you show that you have an ion. You put square brackets and then you put a charge on the top right. That is a sodium ion. Here we have a non-metal. Remember, non-metals like to gain electrons. Look at this. This is oxygen. It's got 6 electrons on its outer shell. It wants a full outer shell. The only way it can do that is by gaining 2 electrons. So when it gains 2 electrons, it now has a full outer shell. So what we need to do, just like before, square brackets around it to show that it's an ion, and we need to give it a charge. What charge is this oxygen ion going to have, guys? What do you guys think? How do you know whether it will gain or lose electrons? Good question. Someone doesn't understand. So basically, if it's a metal, it will always lose an electron. If it's a non-metal, it will always gain electrons. And you can always figure that out by the periodic table. If it's on the left-hand side, it's a metal. If it's on the right-hand side, it's a non-metal. Well done, guys. Everyone's got it. It's going to be a 2- charge. So that's O2 minus. We call this O2 minus. All right. And basically, you can figure out what type of ion you have by looking at the group number. So a group 1 element will always form a +1 charge, just like the sodium I showed you earlier, because it loses 1 electron. A group 2 element loses 2 electrons, so it gets a +2 charge. Group 3, 4, and 5, you don't need to know about, okay? You don't need to know that for your GCSEs. For group 6, that's like the oxygen I showed you here. It gains 2 electrons. That gives it a 2- charge. And then group 7, imagine you have 7 electrons on its outer shell. It needs to gain 1 electron to get a full 8. That gives it a charge of -1. Okay. Yep. Right. So that's how you make ions. How is this linked to ionic bonding? Like I said before, ions, ionic bonding, there's the plus and the minus, they're opposites. It occurs between a metal and a non-metal. So the metal will lose an electron or lose electrons. The non-metal will gain electrons. So what you get is basically electrons being transferred from the metal to the non-metal in order to give both a full outer shell. What you get out of that, let me show you an example. Let's say we have lithium and fluorine. Look at these. Remember, both of these want a full outer shell. Easiest way for the lithium to get a full outer shell is to lose this electron. Easiest way for fluorine to get a full outer shell is to gain an electron. So this electron from lithium needs to go to the fluorine so that they both have a full outer shell. So let's say that happens. This goes here to this position. Now what you've got is 2 ions. This lithium has lost an electron. We put a square bracket to show it's an ion, and we put a plus charge to show it's positively charged. The fluorine has gained an electron. So square brackets around it, negative charge. So now you have 2 oppositely charged ions. You have something positive, you have something negative. What happens when you have something positive and something negative? just like the nucleus and the electron, just like magnets, they attract each other, right? So you have this attraction between the ions. And this here is the bond. That's what's holding the ions together in an ionic compound. The oppositely charged ions have electrostatic attraction, not intermolecular attraction, electrostatic attraction, because you have oppositely charged ions. So when it loses an electron, it becomes positively charged. Yes, correct. And when it gains one, it becomes negatively charged. Those charges come first before the number. No, they come on the top right. You write them on the top right. Do you need to draw the attraction in the exam? Good question. No, you don't. This is just me explaining where the electrostatic attraction comes from. Yeah. So how are you? I'm good. Thank you. When do you know when to say intermolecular attraction? Good question. I'm going to go through that. I've got a page dedicated to that because people always get confused between electrostatic and intermolecular. I'll go through that. All right. Here's another example. Look at this one. We have one electron that needs to be removed from lithium, but oxygen needs 2 electrons. Where is it going to get that second electron from? It can't take this electron because now it's not going to be stable. Remember, lithium needs to be stable. It needs to have a full outer shell. So in order for it to get 2 electrons, it needs, there we go. Dennis has got it. Frozen's got it. Sammy's got it. It needs 2 atoms. So if you've got a scenario like this where one atom can only give 1 electron, but the other atom needs to accept 2, you add another atom in. So here, for lithium oxide, you need 2 lithiums and 1 oxygen in order for both of them to get full outer shell. Look at that. Now they both have full outer shells. All 3 of them have full outer shells, right? So one has gone from the lithium, one has gone from the second lithium, and they've both gone to oxygen. So now what you've basically got is Li2O, 2 lithiums and 1 oxygen, lithium oxide. Okay, so remember I told you, you had a positive ion, you had a negative ion, and there's attraction between them, all right? This is what an ionic compound looks like. Imagine millions of these now, because in real life, you're not just going to have one ion and another ion, right? You're going to have loads. They form this structure, these ionic compounds, these metals and non-metals. This is an ionic compound. You've got the metal here, the blue is the metal, and the non-metal as the orange. We call this a lattice structure. So ionic compounds form a lattice structure, which is basically like a cubic structure. And they can be represented like this or like a ball and stick diagram. So these sticks basically represent the attraction between the positive and the negative ion. That's what's holding everything together. This attraction, remember, I call this electrostatic attraction. This electrostatic attraction is incredibly strong. You need a lot of energy to break this electrostatic attraction. So you need to use that fact to explain a few properties about ionic compounds. So all ionic compounds have very strong electrostatic force of attraction, which leads them to have high melting and boiling points. So sodium chloride is basically salt. That's the salt that you put on your on chips, basically. That, in order to melt that, you need a very, very high temperature, something like a few hundred degrees you need. That's because in order to break these bonds, see all these purple lines, in order to break all of them, you need a huge amount of energy because they're so strong. The electrostatic attraction is so strong. So you would say a large amount of energy is needed to overcome the strong electrostatic forces of attraction between the oppositely charged ions. Another thing you need to know about electrical conductivity. So these ionic compounds, they can only conduct electricity when they're not solid. When they're solid, they can't conduct electricity. In order for something to conduct electricity, it needs to have something that's charged And that thing that's charged needs to be free to move. In a solid, we have all of these ions, but they're all fixed together. They're all stuck together because of the attraction. They're not free to move. But if you were to melt it like this is what they'll look like when you melt it. Then all of these ions will be free to move. And they can carry a charge. So they can conduct electricity. Not only that, they can conduct electricity when they're aqueous. What does aqueous mean? So molten means melted to liquid. So I'm going to write liquid here. What does aqueous mean? Dissolved in water. Well done. So in order for an ionic compound to conduct electricity, it needs to be molten, liquid, or it needs to be dissolved in water. Yeah. Well done, guys. Well done. They're all soluble as well. That's another thing that you need to know. Here we've got a table of the different types of diagrams you can get. They can ask you this in an exam as well. The different diagrams that you can represent ionic compounds with, and their advantages and disadvantages. Sometimes they ask you questions on this. So this here, the thing that I showed you earlier was a dot and cross diagram. Good thing about these is that they show electrons. They're quite easy to draw. The bad thing about them is that they're not 3D. They don't show the 3D arrangement, and they don't show the sizes of the ions properly. These do show the size of the ions, but they don't show electrons. So they're not great in that aspect. They do show the 3D arrangement as well, which is good. But they show gaps between ions. They don't exist. Here we got a two-dimensional diagram. Again, it doesn't show the 3D arrangement of the ions. It can be very complicated as well, but it's very easy to draw. It's probably the easiest one to draw. And then we've got 3D diagrams, which show the 3D arrangement, but they can be difficult to draw, and they don't show electrons as well. So you might get like a 1 or 2 marker just asking you to compare the advantages and disadvantages of these diagrams. Okay. What's the difference between a giant lattice and a simple lattice? Simple lattices are just made up of a few ions or particles. A giant lattice is made up of like millions. So the ions are free to move. Yes, if they're molten or aqueous, they're free to move. Does it have to be water? Can it be any liquid? It can be any liquid, but in GCSEs, you're only going to come across water. It only dissolves in water. Yeah. Good questions, guys. How do you determine the formula of a compound? So like calcium chloride, right? If I told you the word calcium chloride, the compound calcium chloride, how do you figure out that it's CaCl2? So this is a technique called the swap and drop method. I don't know if you guys have heard of this, but what you do is you write the ions down and you swap the charges. So for calcium chloride, let's say we got the question calcium chloride, yeah? You go onto your periodic table, you look for calcium, you see it's in group 2. That will tell you that calcium chloride has a charge of 2+. Remember, I told you any group 2 element always forms a 2+ ion. Then you go to chlorine and you see it has a charge of -1. And what you do is you swap the charges around and you drop them to the bottom. So the calcium, the Ca, will get the 1 from the chlorine, and the chlorine will get the 2 from the calcium. Ca1Cl2. But we don't write it like that. We would call it CaCl2. So calcium chloride is CaCl2. Let me give you guys one more example. Let's say we did sodium oxide. Sodium is in group 1. Sodium has a charge of +1. Oxygen is in group 6. Oxygen has a charge of 2 minus because it's in group 6. We're going to get these numbers, we're going to swap them, and we're going to drop them to the bottom. So Na is going to get the 2 from oxygen, and oxygen is going to get the 1 from sodium. Na2O1, but we don't write ones, so we would call this Na2O. So be familiar with this method, guys. It helps you out with writing formulas. When do you know when you have to do that? When you're writing an equation and you don't know the formula of it. Yeah, sometimes like sodium chloride, let me quickly do sodium chloride, +1 and Cl -1. When you swap and drop them, you just get 1 for both of them, right? So it's Na1, Cl1. That's just NaCl. The ones cancel out. So whenever you're writing a chemical, a symbol equation, and you have a compound which is ionic, you need to do this to figure out what the charge is. Yeah. Yes, it only works for ionic compounds. It only works for ionic compounds. So practice that, guys. If you're not familiar with that. Right, covalent bonding. Remember what I said? I said companions, they share. It involves the sharing of electrons, and the NON reminds you that it happens between non-metals. So when you share electrons, remember the aim is to always get a full outer shell. So here we've got 2 hydrogens. If you were to draw hydrogen, hydrogen would look like this. It just has 1 electron. What's the easiest way for hydrogen to get a full outer shell? Is to get another electron, because it needs 2. It's the first shell, it needs 2 to get a full outer shell. So in order to get that full outer shell, it needs to share it with another hydrogen. And this is how you get your Venn diagram. You put the electrons you're sharing in the middle. So this hydrogen is sharing 1 electron with this hydrogen, which is also sharing 1 electron. Now they both have full outer shells. So if you look at this hydrogen, it's got 2 electrons. So that's a full outer shell. And this hydrogen also has 2 electrons. So that's a full outer shell. They're both very stable. So if you have this set up, what makes this a bond? So remember, in ionic bonding, the bond is between the oppositely charged ions, right? There's attraction there, electrostatic attraction. There is also electrostatic attraction here between the nucleus. We know nucleus is positively charged, right? Both of these are positively charged, but in between them, they have these electrons, and we know electrons are negatively charged. So just like a magnet, this is attracted to the shared electrons, and this is attracted to the shared electrons, and they're all stuck together. That's what makes it the covalent bond. A much easier way to draw them is with a displayed formula, but you see these in organic chemistry more. Displayed formula, where each line represents a covalent bond. What's the empirical formula? That's a Edexcel thing. You don't need to know that for AQA. It's the simplest formula you can get from a compound, the most simplified formula. Can hydrogen lose an electron to go down to 0? Yes, it can. We call that H+. And you'll see that in when we talk about acids, H+ ions. It can form an ion. And that's why it's not in group 1 or group 7. It's in neither of those. It's in its own group because it can form ionic bonds as well. So you feel the overlapping bit first. Yeah. So let's say, let me do an example. Do I have space anywhere here? Oh, we got somewhere. Let's say I do chlorine. Okay. Chlorine, if you look at just the outer shell, it has 7 electrons on its outer shell. 7 electrons. In order for this to get a full outer shell, you need to share with another chlorine. One of these you use crosses for, the other one you use dots for to just differentiate the two. Okay, so this chlorine on the left has 1, 2, 3, 4, 7 crosses. that we need to put in the diagram, and this one has 7 crosses. I would always start with the middle ones, okay? So the one on the left has 7 electrons. How many does it need to get a full outer shell? To make 8, it needs 1 more, right? So what it does is it takes one, or shares one, with the chlorine on the right. So I'm going to take this electron and I'm going to put it here. Then we look at the right-hand side. Again, the right-hand side has 7 electrons. It needs 1 to get a full outer shell. So I'm going to take 1 here and I'm going to put it here. Now you get these 6 remaining electrons and put it on the outside of this chlorine. 1, 2, 3, 4, 5, 6. Now we get these remaining dots and we put it on this chlorine. 1, 2, 3, 4, 5, 6. That's a dot and cross diagram for chlorine. And you can see now, if you count, they both have 8 in them. 1, 2, 3, 4, 5, 6, 7, 8. And this one also has 8. Now they're all stable. That's the formula for chlorine. And these are all the ones that you need to know. Chlorine is in there. And these are the ones which you could just memorize if you don't want to work it out. But you could get asked to apply your knowledge and try and write one yourself as well. 2 non-metals, yes. Any mnemonics? A few memory tricks. Not for this though. Do you have to do a dot and cross? Sometimes you can do squares as well. Doesn't matter which side I put the cross and the dot. No, it doesn't matter. Yeah, it doesn't matter. Instead of a dot, you could also do a circle, by the way. You could do a circle as well. That's fine as well. All right. Now, other ways to represent covalent compounds, 3D structures. You won't get asked to draw these. They'll probably just give you one and they'll ask you to figure out what the formula of this is. So for this, for example, what would you say the formula of this is? We have 1 nitrogen atom in the middle, the orange one, and then we've got 3 hydrogens here. What's the formula of this? There we go, frozen straight in. NH3, 1 nitrogen, and 3 hydrogens. Yes, it's not nitric acid, actually. It is ammonia. Yes, study buddies got it. It's ammonia. It's called ammonia. Yeah. Again, this is the table. Just look at this later. It's straightforward stuff. It's about 3D structures and showing electrons and how easy it is to draw. You could get asked questions just asking you to compare which of these diagrams are better. Now, with covalent bonding, this bit confuses people. You have covalent compounds, okay? There are 3 types of covalent compounds you need to know about. Simple molecular, giant covalent, and polymers, okay? This is where you guys need to listen up because people get confused with the different types of bonds. We're going to start off with simple molecular substances, okay? So these are basically small molecules. So you see that big list I gave you earlier. Where is it? This one. All of these are simple molecular substances. They're made up of small molecules. All right, so if we look at chlorine, for example, remember I said chlorine is diatomic. Between the 2 chlorine atoms, there's a covalent bond. I just showed you, right? With the dot and cross diagram, there's 1 dot and 1 cross in the middle. I'm just drawing the simplified version of this, which is just chlorine like this, okay? So imagine I draw it like that. So we have a chlorine atom here, another chlorine atom here. They're joined together with a covalent bond. So atom and atom. Together, we call these a molecule. So between the atoms, between the 2 atoms, you have a covalent bond. These covalent bonds are very strong. But between molecules, if you had 2 molecules of Cl2, you have another type of bond. These are called intermolecular forces. Molecular means molecules. They're between molecules. These intermolecular forces are very, very, very weak compared to covalent bonds anyway. All right, this is very significant because it tells you why chlorine is a gas, why it has such a low melting and boiling point. All right, so someone asked, when do you know when to use covalent bonds and intermolecular forces and electrostatic force of interaction? I'm going to tell you now. So when you melt these, when you melt anything which is simple molecular, you are not trying to break these covalent bonds. These covalent bonds are way too strong to break. They're even stronger than ionic bonds. Out of all the bonds that you learn, covalent bonds are the strongest. You need a lot of energy to break. Okay. All you need to do is break these weak intermolecular forces. They're very easy to break. They're very weak. You just need a little bit of energy. So, because that's the case, chlorine has a low melting and boiling point because you'd say it has weak intermolecular forces. You don't need to talk about electrostatic forces. That's between oppositely charged things. You don't need to talk about covalent bonds because you're not breaking these covalent bonds here. So that's why they have very low melting and boiling points. And that's why they're mostly liquids and gases at room temperature. If we look at all of the stuff on this list, you'll see they're mostly liquids and gases. Hydrogen, gas, 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 liquid, liquid slash gas, gas. Yeah, they all have very low boiling and melting points because of those weak intermolecular forces. So when it comes to simple molecular, you talk about intermolecular forces because it's got the word molecular in it. I hope that makes sense, guys. What are electrostatic forces? Electrostatic forces is whenever you have something positive and you have something negative attracting each other. So remember the oppositely charged ions I was talking about? Those are electrostatic forces. Anything positive and negative attracting each other is electrostatic. Intermolecular is intermolecules, between molecules. How do the forces overcome? When you heat them up. When you're trying to boil something, you're heating it up, you're adding energy, and it breaks the bonds. How do we know when it's simple? You don't. Everything on that list is basically simple. You know what are giant covalent. I'm about to give you a list of all the giant covalent ones that you need to know. Anything that's not in that list, you can assume is simple molecular. Is the electrostatic what brings atoms together and the covalent keeps them together? The electrostatic bond between the nucleus and the electrons that I was talking about, that's a covalent bond. This attraction here, that is the covalent bond. The shared electron and the positive ions, the positive nucleus. We call that the covalent bond. Covalent bonds are between atoms, so they're stronger than bonds between molecules. Yes, they are. Didn't you say that even covalent has electrostatic between the... Yes, it does, exactly. But we can just... So Coral, you can just say that they're covalent bonds. Yeah, I was just telling you what covalent bonds are made of, how they come about. It is electrostatic attraction, but you can just say they have strong covalent bonds. You don't need to say that electrostatic attraction is strong. Simple as anything but diamond, graphite, graphene, and silicon dioxide. Study buddy, that is perfect. See that? That is something you can use because I'm going to show you all of those 4 things. And simple molecular is basically anything that's not that. Your brain is twisting. I'm sorry to hear that. I'm hoping when you look back on this, it'll make sense. Okay. Okay. Structure of diamond. Yeah, people are asking. So let's keep going. These intermolecular forces are weak and small. Small amount of energy is needed to overcome them. So I've mentioned that already. Now, the other thing about intermolecular forces, I said that they're weak, right? Some are weaker than others. So look at this. These are both group 7 elements. Remember we spoke earlier and we said as you go down group 7, the boiling point increases. And I said that's because they have stronger intermolecular forces. So intermolecular forces are weak, but this one is less weak. It's slightly stronger. It's still not as strong as a covalent bond, but it's stronger. The reason why is because it has bigger molecules. The bigger a molecule, the stronger the intermolecular force. So this explains why iodine, which is in the same group as chlorine, has a bigger boiling point. So iodine has a higher boiling point than chlorine because, this is what you're saying in an exam, it has larger molecules with more electrons, which means it has stronger intermolecular forces than chlorine, and it requires a lot of energy to overcome, or it needs more energy to overcome. Yes, Jathana, if the molecules are bigger, the intermolecular forces are stronger. They're still not as strong as covalent bonds, though, but they're stronger. So 2 atoms is a molecule. Yes, it is. If you have more than 1 atom bonded together, it's a molecule. So that's why long hydrocarbons require greater energy to overcome bonds. Exactly right. Exactly right. And that explains polymers. What are polymers? Polymers are, think of them as really, really big molecules. Yeah, because they're long chains. We come across polymers more in paper 2, but imagine like a really long molecule. They're going to have even stronger intermolecular forces because chlorine is just made up of 2 atoms, right? But imagine like loads of atoms joined up in a chain. This is a polymer. They're going to have even stronger intermolecular forces. Again, not as strong as the covalent bonds between the molecules, between the atoms, sorry, but it's stronger than simple molecular substances. So polymers are another type of covalent compounds. They have a higher boiling point than simple molecular substances. Why don't covalent compounds conduct electricity? So most covalent compounds don't conduct electricity. And I think I'm going to explain it in a second. Yeah. So in order for something to conduct electricity, do you remember what I said earlier? It needs something charged. And whatever that's charged needs to be able to move. Okay? When I talked back about the ionic compounds, the ions were free to move. Ions are charged and free to move, so they can conduct electricity. If you have electrons that are free to move, we call them delocalized electrons, then it conducts electricity. In simple molecular substances like chlorine and iodine, there are no charged particles that are free to move. The electrons are fixed in the atom and there's no ions, so they don't conduct electricity. I hope that answers your question. Are ionic bonds chemically bonded? Yes, they are. Everything we're doing here is chemically bonded. We're doing the topic bonding, right? All right, cool. Sometimes when you draw polymers, you need to draw it like this with a square bracket around it. You just need to simplify it and draw it like this. This is basically, imagine getting this structure inside the bracket and copying and pasting it. Imagine getting that and copying and pasting it. You basically get this, right? Paste, and then we do that again. And you keep pasting it. And what you get is like a really long molecule. And that's the long chain that I'm talking about here. So imagine here now we have that structure, carbon, carbon, hydrogen, hydrogen, and it's bonded to another one, and so on. That's basically what a polymer is. But the way we draw it, it's impossible for us to draw the whole molecule. So we simplify it by drawing brackets around just one repeating unit. And that's basically the diagram that we've got there. And we show it. We have an n there to show that we're multiplying that n times, a certain number of times. Okay, but this is more for like paper 2 in the organic compound section. Giant covalent structures. This is the last covalent structure we're going through. They are compounds which are made up of just covalent bonds, or nearly all covalent bonds. Look at this. Look at how this is different to chlorine. Do you remember chlorine? Chlorine, we had this molecule and we had a second molecule. And between the two molecules, we had these intermolecular forces which are weak. Yeah. And I said the covalent bonds are very strong. Look at this structure for silicon dioxide. This is only made out of covalent bonds, which is like ridiculously strong. So do you expect this to have a high melting point or a low melting point? If it's only made out of covalent bonds, all of these bonds are covalent. Every single atom is joined by covalent bonds. Exactly, frozen. It's going to be extremely high melting and boiling point. Silicon dioxide is basically sand, and you need a very high temperature to melt it. So that is why giant covalent structures generally need a large amount of energy to break the covalent bonds, and they have high melting and boiling points. There are 4 more giant covalent structures you need to know of, and they are the allotropes of carbon. Okay. Let me just quickly remind you guys the differences between electrostatic and intermolecular. Okay, let's just summarize the two. Electrostatic is between something that's positive and something that's negative. Where do you come across it? You come across it in ionic bonding. You come across it in metallic bonding. You do come across it in covalent bonding, but that's only if you're explaining what a covalent bond is. You don't usually talk about electrostatic forces in covalent bonding. Intermolecular, you come across that in simple molecular substances and polymers, mostly. This is between molecules. Don't get the two mixed up because you'll lose marks in your exams for sure. What's metallic? We're going to go through that in a second. We're going to overrun a bit, guys. Sorry, it has to be done. There's so much to go through in chemistry. But yeah, so that's the difference between electrostatic and intermolecular. We're going to go through metallic in a second. Before that, we need to go through the allotropes of carbon. So carbon, the element carbon, can exist in different forms. We call them allotropes. So remember, we learned about isotopes. This is kind of like isotopes, but they're basically the same element, but different structures of the same element. You just need to know the allotropes of carbon. And one of them is diamond. And you'll see here, this has the same shape as silicon dioxide, the one that I just showed you, silicon dioxide. It's got 4 bonds. Every carbon atom is bonded to 4 other carbon atoms. Again, they're all connected with covalent bonds, which means it has an extremely high melting and boiling point because you need a lot of energy to break those covalent bonds. Does it conduct electricity? Remember, for something to conduct electricity, it needs something charged and it needs to be free to move. This doesn't have either. All the electrons are placed within the carbon atoms. It's not free to move. So diamond doesn't conduct electricity. So it has high melting point because of the strong covalent bonds, which need a lot of energy to break. And it doesn't conduct electricity because there's no free moving ions or electrons. 3 bond types. Yes, 3 types of bonding you need to know: covalent, ionic, and metals. Graphite and graphene, yes, you'd classify them as a giant covalent. So graphite looks like this. They exist as hexagonal layers, hexagons. So loads of hexagons in a sheet, but they exist as loads of layers, right? These have carbon atoms, look at this, bonded to 3 other carbon atoms instead of 4. Okay, so imagine getting carbon. Carbon is in group 4. It has 4 electrons on its outer shell. That means it should be able to form 4 other bonds around it, 4 other covalent bonds around it. So that's what happens in diamond. Diamond shares electrons with 4 other carbons. But in graphite, you can see it doesn't form 4 bonds. It forms 3 bonds. 1, 2, 3. For diamond, 1, 2, 3, 4. So because in graphite, there's 1 electron that's not being used for bonding because it's only using 3 of the electrons on its outer shell, this electron is delocalized. Graphite has delocalized electrons which are free to move. That's something that's charged and free to move. So what does that tell us about graphite then? What's this unique property about graphite? It has something charged, the electrons, and they are free to move. What does that tell us? Conducts. The boys got it. It conducts electricity. Graphite conducts electricity. It has delocalized electrons. As well as that, it's a soft material because these layers, remember I said it exists as multiple layers, they can all slide slide past each other. So it's quite a soft material as well. Yeah. So, well done, guys. The other one we have is graphene. Graphene, very easy to remember. It's just one sheet of graphite. Has similar properties. It conducts electricity. It conducts heat as well. Graphite is good at conducting heat as well. And it's used for electronics. Then we've got fullerenes. So fullerenes are another type of allotrope of carbon, but they have hollow shapes. So you can have a spherical one here, which we call Buckminster fullerene. And this is the only one you need to know the formula for. It's got 60 carbons in a ball. So if you see carbons in the shape of a football, that's Buckminster fullerene, and it's got a molecular formula of C60. And then you also have carbon nanotubes, which are carbon atoms in the form of a tube, hexagonal tubes again. So fullerenes, both of these are examples of fullerenes. They're used as drug delivery systems. They're good as drug delivery systems because they can encapsulate other molecules. So in the sphere, you can put like a drug inside and send it to the body. And same with the sphere. Not the sphere, sorry, the cylinder as well. You can put drugs and encapsulate the drug and send it into your body. So it's useful as that. And it's also, so drug delivery, it's also useful as industrial catalysts because they got high surface areas. Carbon nanotubes are used for electronics again, and they're used in tennis rackets or materials where you need them to be strong with not a lot of mass. So they have a high tensile strength. So things like tennis rackets they're used in as well. High melting point, yes, they do. Which revision guide companies do I recommend? Flash Revision Lab, CGP. Go for CGP as well. Can you send the link for the cram classes before the lunch again? Yes, I will do that. When's the lunchtime? Lunchtime's coming, guys. Bear with me. Bear with me. Memory trick for difference between diamond and graphite, guys. Diamond. Let's draw a diamond. If you draw a diamond, look at how many sides it's got. 1, 2, 3, 4. 4 sides. That means it forms 4 bonds with every carbon. Every carbon forms 4 bonds. Okay. Graphite. Graphite. It's got T, H, R, E. T, H, R, E. Almost says 3. You can say 3. It forms 3 bonds with every other carbon atom. That's the closest I could get with this memory trick. The H in graphite reminds you that it exists as hexagons as well. And there was something else as well. Or yeah, those are the main things. There was more in it as well, but I think it'll be more useful if you guys watch the video. So use this QR code, guys. I've got a full video on it. I've got animations and everything, and it basically tells you how to see the differences between diamond and graphite. Okay. Nanoparticles, yes, that will come up. That's a triple topic. All right, last one, metallic bonding. Metallic bonding is the last type of bonding you need to know. The easiest type of bonding, there's not much to know about this, okay? First thing, it occurs between metals. That's obvious because it's metallic bonding. What is it? It's positive metal ions surrounded by a sea of delocalized electrons. That's what you need to say, okay? So metal ions, this is the diagram you see in exams all the time. I just made it colorful. Positive metal ions, and it has a sea of delocalized electrons. These electrons, these little yellow particles are electrons, and we call it a sea because it kind of floats, it flows through these metal ions. Think of it as like this whole thing being a river. Imagine this a river. In the river, you've got these stepping stones. Those are the positive metal ions, and the electrons flow through it. And because the electrons can flow through it, they're delocalized. It means metals can conduct electricity. Remember, if you have something charged and it's free to move, it conducts electricity. So metals conduct electricity because they have a sea of free moving electrons, a sea of delocalized electrons that are free to move. This is metallic bonding though. What's holding everything together? It's something that's positive. So positive ions are positive and electrons are negative. What type of attraction is this, guys? Let's see. What type of bond is this? Let's see if you guys have learned anything. Is this intermolecular or electrostatic? Is this intermolecular or electrostatic? You've got a positive metal ion and a negative electron. Boom, you guys have got it. Why is it electrostatic? It is electrostatic. And why is it not intermolecular? Oppositely charged, yes, but not ions, Safa, not ions. They're oppositely charged particles, positive metal ions and negative electrons. Oppositely charged, they're attracted. They're like magnets, electrostatic. Intermolecular is between molecules. Thank you, guys. This is good. It's showing me that you guys are learning stuff, which is always a plus. Properties of metals. They have high melting and boiling points. It's very hard to melt a metal. Again, strong electrostatic forces of attraction. It needs a lot of energy to overcome. That's why they have high melting points. Okay, so it's like ionic bonding. Strong electrostatic force of attraction, but it's not between oppositely charged ions. It's between the positive metal ions and the delocalized electrons. That requires a lot of energy to overcome, so it's very hard to melt a metal. So generally, they're solid at room temperature. They conduct electricity. Yes, I've said that already. They've got delocalized electrons. They're also good at conducting heat. Again, that's because of the delocalized electrons. Not only does it carry a charge through the structure, it can also carry thermal energy, heat. That's why metals are used in like cooking. Also, they're malleable. You can easily change the shape of a metal, a pure metal, because like you can push the layers. They exist as layers, and these layers can slide over each other. So if you apply a force to the top layers, they can slide over the bottom layers and change the shape of the metal. But if you want to stop that from happening, you can turn them into alloys. Alloys are basically just mixtures of metals. So imagine getting that same metal but adding like another metal in it. So these are these dark gray circles. Can you guys see now? They're not in layers anymore. So we've just disrupted, we've distorted the layers. You can't just push the top and expect it to slide. So if you want to make a metal stronger, you can just add, or you can just mix it with another type of metal. Does that mean gold is a pure metal? Pure gold, you can easily shape. That's why Rutherford used it in the gold foil experiment. What you guys have as jewelry, if you have any gold jewelry, it's probably an alloy, unless it's like 24 carats. It's an alloys mixed with something else. That's why it's a bit harder to break. So the atoms are different sizes and it's harder to distort it. Yeah. If something's a good conductor of electricity, does it mean it's a good conductor of heat? Yes, pretty much. Yes, yes. So alloys are not malleable, correct, because their layers aren't free to slide over each other. All right. Okay, very, very last thing. Very easy. Solids, liquids, and gases. Okay. Difference between them. Solids have particles which are packed together. Liquids still packed together a bit further apart. Gases, the particles are further apart. Solids are arranged regularly in layers. Liquids are not. They're free to flow past each other. Gases move in all directions very quickly. Gases can be compressed. Liquids and solids cannot. Okay, you need to know the differences between them. You also need to know how to write state symbols. Solid is an S, liquid is an L, gas is a G. Aqueous, I mentioned that earlier, means it's dissolved in water. All acids are aqueous. You need to know these processes that you learn in physics as well. So to go from a solid to a liquid, you call that melting. From liquid to boiling, you call that boiling. Sorry, liquid to gas, you call that boiling. Gas back to liquid, you call that condensing. And liquid back to solid, we call that freezing. So when you heat a solid, you can do that. And when you cool it down as well. This section here is just about breaking bonds using forces, using heat. And we've mentioned that already when we were talking about the bonding. If you have strong force of attraction, you need a lot of energy to break, which is why some things have a higher melting point. They need more energy to change state. So you need to be able to do that and also be able to predict the state of something if they give you melting and boiling points. So like, for example, if they told you, what is the state of water at 50, let's say 102 degrees, yeah? Its melting point is 0. So anything below 0 is going to be a solid. Anything between 0 and 100 would be a liquid because 100 is the boiling point and melting point is 0. And anything above 100 is going to be a gas. So 102 is bigger than 100, so you'd say it's a gas. Those are some types of calculations that you'd be expected to do there. Okay. All right. How are we doing? Okay. Triple guys, unfortunately, you're going to have an even shorter break. Combined guys, we're going to keep this break until 1:15. Okay. So we'll be back at 1:15. Triple guys, your break will probably be about half an hour, unfortunately, your lunch break. So it's going to be a short one. So combined guys, I'll see you in 45 minutes at 1:15. Why is the break so short? It's meant to be an hour, but chemistry has a lot more topics in it. I don't mind giving a longer break and then finishing later as well, but it's down to you guys. You guys can let me know what you'd rather do. Longer break? Would you guys rather have a longer break and finish a bit later than 3:30? I'm getting both answers here. All right, let's see. Maybe this one I'm going to keep. This one I'm going to keep at 1:15 because I've already told the combined people to go. I'm going to keep the breaks short, and we'll see in the next one because there's quite a bit to do in the next one with the calculations. I will try and I'll try and make everyone happy. But yeah, we'll be back at 1:15, guys. Triple guys, I'll try and do this as fast as possible. Nanoparticles. And I want to go through fuel cells as well because let me think. Fuel cells. No, I could go through fuel cells later. Nanoparticles. So there are 3 different types of particles you need to be able to identify. We've got coarse particles. You need to know what sizes these are. So anything between 10,000 and 2,500 nanometers are called coarse particles. We also call them dust. Nanometers is basically 1 times 10 to the minus 9. Okay, so let me write this down here actually. 1 times 10 to the minus 9 meters is equal to 1 nanometer. If you have a particle between 100 nanometers and 2,500 nanometers, we call that a fine particle. And nanoparticles are anything between 100 and 1 nanometer. So you need to know those factors, those numbers. Properties of nanoparticles. They have a high surface area to volume ratio. Do you guys remember these cubes from biology? It's exactly the same calculation. In biology, we did a surface area to volume ratio, right? We used easy numbers. We used 1 and 2. In chemistry, they're more likely to give you more difficult numbers. So you need to work out the volume of this cube. So length times width times height. So you do 100 cubed. That gives you 1,000,000. Then for surface area, you work out the area of one face. So that's 100 times 100. And then times it by the number of faces, which is 6. That gives you 60,000. So surface area to volume ratio in chemistry, what you usually do is you divide the surface area by the volume. You don't write it as a actual ratio, but you can still get marks for writing as a ratio. But sometimes they'll ask you to divide the 2 numbers. So if they do that, you'll get 0.06. If you were to do the same thing for a smaller cube, you would find that the surface area to volume ratio is much bigger. It's 0.6, not 0.06. So what we're trying to say here is the smaller a particle is, the greater the surface area. So that's why nanoparticles are so effective. They have a huge surface area to volume ratio. So because of that, we have loads of different uses for them. They're used in medicine, they're used in electronics, deodorant, cosmetics, and sunscreen. You basically need to be able to list these and why they're the case. So like nanotubes, we've already talked about. They're used for drug delivery. Electronics, again, nanotubes can conduct electricity because they've got delocalized electrons. Deodorant, because they have antibacterial properties. So some of them can have properties that kill bacteria. They can stop odor from the body. And then for cosmetics and sunscreens, specifically sunscreen, because it has a high surface area to volume ratio, you can use a small amount to cover your whole body. You don't need to waste the sun cream. They're used as catalysts to speed up reactions as well, because catalysts have a high surface area to volume ratio as well. The negative to nanoparticles is that because they're so small, they can cause cell damage. They can get into your body. They can be harmful to the environment, and they're very, very expensive as well. So you need to go the advantages and disadvantages to those. Wow, wow, wow. Topic 2 done. So what do we have left? We got quantitative chemistry. We've got chemical changes with electrolysis. We've got a lot to do, guys. But go and have your lunch, guys. I'll see you all at 1:15. Have a great lunch. Have a nice rest. See you in about 35 minutes. You don't need this in depth. No, not too much. You don't need to know it too much. We've got nano. Yeah, we've got nano and fuel. So fuel cells, you mean? Fuel cells, yeah, we'll do that after electrolysis. Fuel cells, you don't need to know in a lot of detail. All right, guys. PM is just an abbreviation. It doesn't really come up much in exams. You love chemistry more than lunch. Love to hear that. Guys, go and enjoy your lunch. See you at 1:15. Welcome back, guys. How was your lunch? What did everyone have for lunch? I know it wasn't that long, especially for you triple guys, but we got a lot to get through. Just a reminder, guys, cram classes will be happening the day before your exams, um, the day before every one of your exams, just the evening before. We're just going to be going through um, things to get you guys ready the day before. So sign up to those if you haven't already, and we'll spin a wheel, and one of you guys will get free access to those as well. Paper 2 classes. So this is going to be the last free paper 1 class, guys. So next one is a paper 2 class next Tuesday. So remember to sign up to those as well if you guys are interested in those. It's going to be the same format, but for paper 2 content. Spaces are limited, so if it does reach a certain amount of if we do get a certain amount of signups, then we'll probably close them as well. So if you are interested, then yeah, try and sign up soon if you do. Chicken nuggets, Jada Martin, like to hear that. Burrito. Curry. What's the difference between cram and bootcamp? So this will be more focused towards the actual, like, just getting you guys ready for the exam itself. All right. So we'll be giving you guys tips on like answering exam questions. We will go through content as well, mostly content, because the day before exams, that's what you really want. You do need to do your exam questions as well, but there's a lot of content for you guys to remember. So the day before, we'll try and cover as much of that as possible. Someone had hydrogen for lunch. Interesting. Okay, cool. Still a lot to go through, guys. I think the order I'm going to do it now is we're going to do topic 3 first, then topic 5. We're going to jump to topic 5 and we're going to go to topic 4 right at the end, because that's the one with electrolysis. I imagine that's the one that people are going to have the most questions on. So I'm going to leave that to the end. I think that'll work the best. But let's see how we get on with time. Quantitative chemistry. This is the one which is calculation based. This is another one people don't like. A lot of mole calculations. Hopefully, I make things easier with this session. If you want to sign up to paper 2, guys, we'll drop the link. Can one of the moderators drop the link? Joan, can you drop the link on the chat, please, at some point? And you guys can sign up for that as well. Cool. So quantitative chemistry, calculations. First one, relative formula mass. We've already talked about relative atomic mass. I've shown you how to calculate relative atomic mass. Relative formula mass is just the sum of relative atomic masses. So you find those in the periodic table and you add them up. So here we've got calcium fluoride, CaF2. So that means you've got 2 lots of fluorines and 1 lot of calcium. 1 lot, just 1 calcium, let's say that. You get the atomic masses, the relative atomic masses of each. So that's 40. Fluorine is the bigger number, 19. There's 2 lots of that, so you do 19 times 2, add them together, and that will give you an answer of 78. Make sure you practice how to do this. Relative formula mass, calculating relative formula masses, also known as MR. Whenever you want to calculate the MR of something, you just add up each of the relative atomic masses. Here we've got several examples you guys can try out. So what I would do is cover up the calculation and the MR, and then go one by one if you struggle on this, and try and work out the MR and see if you're getting the right answer. Right? So next, percentage mass of an element in a compound. This is another math style question as well. If you were asked, for example, this is the question: what is the percentage of lithium in Li2SO4? You can think of it as a formula, or you can just use your math skills here. How much lithium is there in here? All right, so let's think about that. We've got 2 lots of lithiums. We've got 1 sulfur, and then we've got 4 lots of oxygen, right? So what we need to do is to find this as a percentage. you do the 2 lots of lithium. So you do 2 times the AR of lithium, the atomic mass of lithium, which is 7, and we're timesing it by 2 because there's 2 lithium atoms, divided by the MR of the whole thing of lithium sulfate. And I just showed you that you just add everything up here. So that's going to be 7 times 2, 2 lots of 7, plus 1 sulfur, plus 32, plus 4 lots of 16. 4 lots of 16. And we want this as a percentage, so we just multiply that by 100. All right. So you can just use math skills to do this, or if you want, you can memorize this equation, because remember, you don't get any equations in chemistry. You just need to apply it to whatever compound it is. In your exams, it's not going to be lithium sulfate. It's going to be something random. They're going to say, find the percentage of sodium in sodium sulfate or something. So what you would need to do is work out the atomic mass of sodium. That will be in the periodic table. Multiply it by how many sodium atoms there are. So you see whether it's Na2 or just Na. Then you divide it by the whole MR. You add up the atomic masses of everything in there. Okay. Why am I timesing by 2? Because there is 2 Li's. Let me write this a bit bigger. It's Li2SO4. All right. If it asks you what's the percentage of sulfur, you wouldn't times by 2. You would just do the 32 on the top times by 1, because there's only 1 sulfur. If you were asked for oxygen, you do 4 times 16, because there's 4 lots of oxygen. And you just follow that. Again, we've got loads of questions for you guys to practice here. This topic is all about practice. It's math skills. So do practice them. If you're struggling with them, try a few and see if you get the final answer. Cover up the first few, the last few columns, and work out, for example, this one is work out how much nitrogen there is in ammonia, and they've told you it's NH3. So you'll do nitrogen, there's only 1 nitrogen, so that's 14. If you look at the periodic table, over 14 plus 3 lots of 1, so 14 over 17 times by 100. Okay, so that's how you do that one. What's the difference between relative formula mass and relative atomic mass? Relative atomic mass is the thing that you find in the periodic table. Remember, we did that in the first topic, how to calculate it. That's when you do the mass numbers times the abundances and divide it by 100. So relative atomic mass, the AR, you find in the periodic table. Relative formula mass, or MR, you work out by adding up all the relative atomic masses. Remember all the formulas. No, there's not too many, but let's see if we can come up with any. Safa, that's good to hear. Quantitative chem is fun. Okay, that's good. Glad you like it. Yeah, okay, cool. Conservation of mass is another concept you need to know about. So if you guys came to the physics paper 1, you'd know about the conservation of energy. Energy can't be created or destroyed. Conservation of mass is the fact that mass can't be created or destroyed. In a reaction, if you start off with a specific amount of mass, you should always end up with the same mass at the end. Mass cannot be created, mass cannot be destroyed. Okay, so you can see that when you balance the equation. Here we have 2 calcium atoms. At the end, we have 2 calcium atoms. At the start, we have 2 oxygen atoms. At the end, we've got oxygen times 2 oxygen atoms at the end as well. You can also see that when you weigh the mass of something. So the total mass of the reactants should equal the total mass of the products, always. Sometimes it seems like it doesn't. So like this reaction, for example, if you were to get 9 grams of sodium and you were to burn that in oxygen, you would find, so imagine you got like a spatula, not a spatula, let's say you got a test tube with sodium in it, and then you reacted it with oxygen, it would appear to increase in mass. The mass of it would increase to 13 grams. And people would think, oh, mass has just been created. But no, that's not the case. Mass cannot be created or destroyed. What's actually happening is the mass of the oxygen is being added to the sodium. So the oxygen's in the air. You can't weigh the oxygen. But when you react it, whatever mass it is gets added onto the sodium. So in this case, it would be 4 grams. You can't weigh that on a mass balance. But that's the reason why the mass of the final product increases. Then we have the opposite. Sometimes mass appears to decrease. If you've got calcium carbonate and you heat that up in a test tube, so you weigh it and it's 23 grams, the calcium oxide you get at the end of it will be lower. It'll be like 17 grams. And people would think it's lost mass, but no, it hasn't. The mass has just escaped from the reactant. So you've got about 6 grams here, which has just floated away into the air. So when you weigh it, you can't measure it. So that's the conservation of mass. Mass has to always be conserved. Now, this next bit is about chemical measurements. And it's useful not just for chemistry, it's useful for physics and biology as well. Errors. There's 2 types of errors that you guys need to know about: random errors and systematic errors. So random errors, when you're carrying out an experiment, you can have human errors or some conditions just slightly changing. Like, for example, the temperature of the room might slightly change, and you can't really do anything about it. Okay, so these can cause slight fluctuations in your answers. So to fix this, what you can do is take loads of measurements and calculate a mean. So if you do the experiment over and over again and calculate a mean, you reduce the effect of a random error. Systematic error is something where you have an issue with the measuring equipment. There's something wrong with whatever it is you're using to measure your reactant or product with, and that causes a consistent error. So your value is always too high or your value is always too low. An example of this, you might have heard of this, is a zero error. So imagine you're weighing something, and before you even add the thing you're trying to weigh, the mass balance says 0.3 grams or kilograms. Okay, so even before you've added anything, it's giving you a reading. That's obviously wrong. It should say 0. So then when you add an object on it, and then it gives an answer of 10.3 grams, you would basically have to subtract the 0.3 from it. That's called a zero error. And you can basically fix it by subtracting the value that you had at the beginning. So a zero error is an example of a systematic error. Now, this can lead to uncertainties. You guys might have heard of uncertainties. Has anyone never heard of uncertainties? This is when you get a number like this. Have you guys seen this before? It barely comes up in exams, but you might get like a 2 or 3 marker in it. Yeah? Yeah, exactly. GCSE student. So we've got uncertainty here. So let's say we just weighed the mass after a certain experiment, okay? And these are the answers that we got. We got 11 grams, 13 grams, 17 grams, 14 grams, okay? And we wanted to work out the mean with the uncertainty. What you would do, first of all, is you would add them all up. If anyone's got a calculator, can someone do this, please? 11 plus 13 plus 17 plus 14 divided by how many there are. This will give you the mean. So to find the mean, you just do the normal stuff, right? You add them all up and you divide it by how many there are. Once you've done that, you can work out the uncertainty. The uncertainty tells you what the value you just wrote could be as a range. So what's the highest possible value it could be, and what's the lowest possible value it could be? Thank you, guys. So for example, this one is 13.75 grams. Okay, that's the mean, but there is some uncertainty to it. We don't know whether that is the true value. That true value could be within a range. And to work that out, if they ever ask you to work out the uncertainty, you get the highest value, you minus the lowest value, that's called the range, and you divide it by 2. All right. So in this case, we would get the highest value, which is 17. You get the lowest value, which is 11. So subtract those 2 and divide it by 2. So 17 minus 11 gives you 6. 6 divided by 2 is 3. So basically, that's the uncertainty. And we would write the final thing as 13.75 plus or minus 3 grams. That basically tells us this value could be 3 grams bigger. So it could be 16.75 grams if you were to add 3 onto 13.75, or you could subtract it to get the minimum value. It could be 10.75 grams, anything between these two values. Okay, the mean is this, but it could be anything between these two values. That's how uncertainty works. So the mean is 13.75. The uncertainty is plus or minus 3. Yes, well done, well done. Right. Everyone's favorite topic, moles. A mole, what is it? It's a way to measure the amount of a substance. So we can use grams to tell. So for me to tell you how much carbon I have in my hand, I would say I have 3 grams. Or I could also say I have 1 mole. It's just a way of you expressing the amount of a substance. The units for it is mol, mole, very simple. The definition of it: if you ever have 1 mole of any substance, no matter what it is, it always has the same number of particles in it. And that is known as Avogadro's constant. It's 6.02 times 10 to the 23. So 1 mole of any substance always contains that many particles. So if you had 1 mole of carbon, it would have 6.02 times 10 to the 23 particles. If you had 1 mole of water, it would have 6.02 times 10 to the 23 particles, molecules. That's one way of defining what a mole is. So 1 mole of any substance always has that same amount. The other thing you can say is that 1 mole of any substance has the same mass as its MR. So if you know the MR of a substance and you have 1 mole of it, that's how many grams of that substance you have. Let me explain that a bit better. If you have 1 mole of carbon in a test tube, you look at what carbon is in the periodic table, you look at what its relative atomic mass is. Its MR is 12, or its AR is 12. So that means 1 mole of carbon has 12 grams in it. If you did water, 1 mole of water, you find the MR of water is 1 plus 1 plus 16 because it's H2O, so H plus oxygen, that's 18. So 1 mole of water has 18 grams in it. So that's how you can work that out. This comes up in combined and triple science. What does mole mean? I hope I just answered that question. Yeah? Avogadro's constant. 1 mole equals to the AR or MR. Yes. Yes. Or you can say it has the same number of particles as Avogadro's constant. Here's the equation for moles. I'm sure you guys have used this in school. Moles equals mass over MR. You need to be able to use this equation quite a lot. We've got an example here that uses it. Find the number of moles in 32 grams of methane. So what we will do here is we would work out the MR of methane is CH4. If you look in the periodic table, C is 12, H is 1. There's 4 lots of 1 because it's CH4. So we do 12 plus 1 plus 1 plus 1 plus 1. That gives you 16. So there's 16 as the MR and 32 as the mass. We do mass over MR, so that's 32 over 16, which tells you you have 2 moles of methane. So 32 grams is 2 moles, all right? Again, this comes with practice, guys. So I've got several examples you guys can try out if you want to practice this. 15 grams of ethanol, you do the same thing. Work out what the MR is, and then do mass over MR, and you'll get the number of moles. Sometimes they might ask you to rearrange that equation. If you want to work out the mass, guys, what's the equation? Mass is equal to what? Let me know in the chat. If you rearrange this equation to make mass the subject. Do they give you the grams? It depends on the question. They will tell you the mass usually, yeah, if they want you to work out the moles. Well done, guys. Everyone's got that. Moles times MR. So if you want to rearrange the equation, you can use the triangle if you want. Put mass at the top, moles at the bottom, and MR at the bottom. Yes, so mass is equal to moles times MR. So in this question, find the mass of 3.5 moles of ammonia. Again, we want to work out the MR of ammonia. Nitrogen is 14. Look that up in the periodic table. Hydrogen is 1. We've got 3 lots of 1. That gives you 17. So we can do 17 times 3.5, and that gives you 59.5 grams, right? Again, we've got loads of examples for you guys to try. So just work through those if you guys struggle with these questions. All right, what gets confusing now is questions involving moles with chemical equations, okay? But I'm going to show you some steps here that you can use whenever you have a question like this. So the question would look something like this. They will give you a mass, and they'll give you a reaction as well. And they'll ask you to calculate a mass, calculate the mass of sodium oxide. All right. There's 3 steps I want you guys to follow. You don't need to follow these steps. You might have been taught it differently in school. Yeah. But this is how I always teach my students. Okay. You have 2 things, the known and the unknown. The known is what you know the mass of. The unknown is what you're trying to find out. And the steps that you want to follow is CRU, K-R-U. All right. So your first step is to identify what the known and the unknown is. What do we know the mass of? If we look at this question, this is the question that we're doing. We know the mass of sodium. There's 46 grams of sodium. All right. So what I'm going to do is I'm going to put a K for known in sodium. I'm going to put a K there. Unknown is what we're trying to find out. What is the question asking us? It's saying calculate the mass of sodium oxide formed. So let's go to sodium oxide and let's put a U here. I always tell my students to do this so they don't get confused, but you don't need to do it. If you're really good at mole calculations, you don't need to follow it. What was the known? What was the mass that we knew? Let's go back. It was 46 grams, the question says. So we have 46 grams of sodium. We want to work out how many grams of sodium oxide we have. So first step in CRU, the K is for the known. We want to find out the moles of the known. So we use our equation. Moles is equal to mass over MR. Right? What's the mass? The mass is here, 46 grams. 46 grams over the MR of sodium. So look that up in the periodic table. Most questions, they'll tell you what the ARs and MRs are in the question, which makes it easier. Sodium is 23, I believe. So we're doing 46 divided by 23. 46 divided by 23 gives you 2. So that means we have 2 moles of sodium. 2 moles of sodium. Good question. Why do we not times it by 4? When you're doing this step, you don't use the big numbers. All right. So this 4, this 2, you don't use it in the known step. You only use that in the second step, the ratio step. This is why in CRU, Can you guys see? I've only made the R a big R. I've made the K small and the U small to remind you that you don't use the big numbers for the first step and the last step. You only use the big numbers for the middle step, the ratio step, which I'm going to show you now. So the MR, you don't use the big numbers. You only use the small numbers. Ratio step here is where you use the big numbers. So you want a ratio of your known to your unknown. So you look at the two numbers in front. We've got a 4 here, and we've got a 2 in front of our unknown. So that's a ratio of 4 to 2. We can simplify that. 4 to 2, if you divide both sides by 2, is 2 to 1. We have 2 moles of sodium, we just calculated. So of our known, remember our known is sodium and our unknown is Na2O. So 2 moles is our known. We're going to put that here. We've got 2 moles of sodium. So that means how many moles of sodium oxide do we have? We have half of that. So that's going to be 1 mole of sodium oxide. Because it's a 2 to 1 ratio. That's the second step done. Then for the final step, once you've got the moles, the U is for unknown. You have to work out what the unknown is. What is the question asking? It's asking us for the mass of sodium oxide. So we rearrange that mole equation, and that gives us, like you guys said earlier, mass is equal to moles times MR. Moles times MR. So we get our 1 mole, which we just calculated, times that by the MR of Na2O. I'm going to work out the MR of that. Na is 23. There's 2 lots of 23 because it's Na2O. Plus oxygen is 16, if you look at that in the periodic table. So this is basically what we're doing. Put that all in your calculator and you'll get the final mark. Notice again, guys, I didn't use the big number in this step. I didn't times it all by 2. You don't use that to work out the MRs. And that's a small u to help you remember that. So final answer, there we go. GCSE Study Accounts got it. Jada Martin's got it as well. Well done, guys. Final answer is 62 grams. You just follow those steps, the crew steps. So we have so many examples for you guys to try out, to practice that. So please practice it. Practice it out. We've got it on our website as well. We've got loads of examples you guys can try out. So crew, keep using that. We're going to see that again at some point as well. So I'll come back to it in a second. Okay, another type of question. Is it always in grams? Sometimes it's in kilograms. You might need to convert. Okay, this equation is for grams. You actually get it. That's great to hear. Okay, another type of question you can get. This doesn't come up that much, but you could get asked to balance equation using moles. It's a bit of a weird question because you can just balance this normally, but they sometimes ask you to use moles to balance it. So I'm going to show you the steps that you need to do. Okay, so look at this question. 6.35 grams of copper reacts with 16 grams of oxygen to form copper oxide. Balance the equation. They'll give you an equation. So that's your copper, that's your oxygen, that's your copper oxide, by calculating the moles of the reactant and products. So what I've done here is I've written out the equation and I've written what's in the question. 6.35 grams here and 1.6 grams here. We need to work out how much CuO there is. How do we work that out? We use, remember the conservation of mass. Mass can't be created or destroyed. So whatever mass we have here should be equal to the mass we have in the products. So 6.35 plus 1.6 should give you the mass of copper oxide. That's your first stage, 7.95 grams. So we basically have 3 columns of calculations that we need to do here. Your next step is to basically work out the MRs of each. So work out the MR of Cu, just look up in the periodic table, that's 63.5. work out the MR of O2, not just O. O is 16, O2 is 32. And then CuO, we add Cu to oxygen, that gives us 79.5. The reason we're working out the MRs here, so we got mass, we worked out MRs, that's because we're going to use the mass and the MR to work out the moles in the next stage. So the next stage is to work out moles. So that's going to be doing mass divided by MR every time. Mass over MR, mass over MR, mass over MR. So you do that separately in 3 different columns, and you've got 0.1 when you do 6.35 over 63.5, then 0.05, and then 0.1 here. This is basically a ratio that we have. Remember what we're trying to do? We're trying to balance the equation. This is going to tell us what number to balance it with. Now, this isn't useful because we can't balance something with a 0.5 in front or a 0.01 or 0.05 in front. You have to have like a 2 or something like that, right? So we want to simplify this ratio. In order to do that, you divide all 3 numbers, so the 0.1, the 0.05, and the 0.1, you want to divide them all by the smallest value. So I'm going to write that here on the side, divide by the smallest value. When you divide by the smallest value, you get numbers which are much more manageable. So for example, 0.05 is the smallest value out of these 3. So you divide all of them by 0.05. So see here, I've got the 0.5 dividing the 0.1. Then we've got the 0.05 dividing by itself. And then we've got this 0.1 dividing by its 0.05. And when you do that, you get these round numbers, a 2, a 1, and a 2. And you can use those numbers to balance the equation. So it's going to be a 2 in front of the copper and a 2 in front of the copper oxide. Do we always have to simplify? Yeah, because you can't put 0.1 or 0.05 in front of the compounds in here. You can't write those. You have to write whole numbers. You can put halves, but you can't do anything else after that. You can use a grid method. Are we doing spin the wheel? Yes, we are. Right at the end, we're doing spin the wheel. Can I explain step 4 again? Yep. So once you've worked out the moles of each, yeah, you want to simplify this. Having a ratio of having a ratio of, what was it, 0.1 to 0.05 to 0.1 is not good. You can't be putting 0.1 here. You can't balance that with a 0.1 or a 0.05. You have to use whole numbers. You can put halves, but you can't put numbers like this. You want whole numbers. In maths, if you want to make this a whole number, you divide all of them by the smallest number. So you divide each one by the smallest out of the 3, which is 0.05. So I'm just dividing all 3 by 0.05. And if you put that in the calculator, you get that's 2, that's 1, and that's 2. Does that make sense? And then you put that as the balancing terms there. Yep. Okay, cool. Last type of calculation you can get is limiting reactants one, which is the hardest type of calculation you can get. And this is the one that people lose marks on the most. In order to understand this, you need to know the difference between an excess reactant and a limiting reactant. So imagine you're reacting 2 things. Let's say you're reacting hydrochloric acid and sodium hydroxide, okay? Or let's look at what we're doing here. No, let's do the example I just said. So hydrochloric acid plus sodium hydroxide, okay? When you react those 2, it forms sodium chloride plus water. Why did I put 2 there? Let's see, NaCl, sorry. Now, imagine we had 10 grams of this and 10 grams of this, okay? Let me talk in moles because we're doing moles. Let's talk in moles. Let's say I had 2 moles of this and 2 moles of this. These 2 reactants are equal. They're going to perfectly react together. And there's going to be none left over, okay? So that's like having, let's have a ball for each mole that I'm talking about. We have 1 mole, 2 moles here, 2 moles here. So each mole is going to react. So at the end of these, because they're all reacting, you end up with no moles at the end. So you're going to have no HCl and no NaOH at the end. But imagine we did it a different way. Imagine we had 3 moles of hydrochloric acid and only 1 mole of NaOH reacting. What's going to be left over there and what's going to be fully gone? What do you guys think? I'm just saying, what if we're choosing how, imagine you have 2 beakers, we're choosing how much NaOH and how much HCl we have, and we're choosing to have 3 times more HCl than NaOH, and we react it together. What's going to happen at the end? Exactly, HCl is going to be left over because one of these moles is going to react with one of these moles of NaOH to form 1 mole of this and 1 mole of that. So all of the NaOH is gone because it's reacted, but some of the HCl is going to be left behind, right? So we call this the excess reactant. The excess reactant is what you have more than enough of reacting. You have more than you need to react. We had 3 moles. We only needed 1 mole for reacting, but we had 3 moles. We had 2 moles extra. The limiting reactant is the one that gets fully reacted because you have less than needed or you have just enough to react. So NaOH is the limiting reactant because it's all going to disappear because the HCl is going to overwhelm it. So that's the difference between the two. Excess, you have more than required for the reaction. It's left behind. And then we have the limiting reactant, which is fully reacted. Okay, and if you know how many moles of your limiting reactant you have, that's also the amount of product that's made. So because you had 1 mole that got reacted there, you got 1 mole of the products made. So let's look at these notes here. So it says excess, you have more of it than needed to ensure the other reactant is completely used up. The limiting reactant is completely used up before the excess reactant. So when the limiting reactant gets used up, so that NaOH gets used up, it stops the reaction. Yeah, because there's no more reactant to react. That means the HCl is just left behind. The amount of product that can be formed depends on the amount of limiting reactant. So remember, I said at the beginning we had 1 mole of NaOH. That means we can only form 1 mole of product as well. That's what that statement means here. Where did I say it? The amount of product that can be formed depends on the amount of limiting reactant. The limiting reactant is always the number that should be used, and it indicates the maximum possible amount of product that can be formed. So we use 1 mole of NaOH, therefore we formed 1 mole of NaCl and H2O. Now, how do we determine the limiting reactant? This is the confusing bit. Look at this. We have a reaction, 30 grams of silicon dioxide reacting with 20 grams of H2F2. Which of these is limiting? Now, be careful here. People are going to look at this and straight away say it's H2F2. Well, you're not, because the answer is just underneath and you'll see it's not. But loads of people would think that H2F2 is the limiting reactant. But in order to figure out what the limiting reactant is, you need to work out the moles. You can't compare mass. You have to compare moles. You always need to convert to moles. So how do we do that? Remember, we do moles is equal to mass over MR. So we look at each of these reactants separately. We work out their MRs by adding up their ARs. So SiO2 is 60 because we add up silicon and 2 lots of oxygen, and H2F2 is 40. We add up 2 H's and 2 F's. Okay, so Now we can work out the moles because we've got mass here and we've got MR here. So we do 20 over 40 here and we do 30 over 60 here. We have 0.5 moles of SiO2, 0.5 moles of H2F2. So people might think because we have equal moles, that means there's no excess, there's no limiting factor here because they fully react. But what you also need to look at is the ratio in front. Look at what this says. This says for every SiO2, you need 2 lots of H2F2 for this reaction to happen because we've balanced the equation. That's the case. So that means the H2F2 needs to be 2 times bigger for this reaction to happen. So if you have 0.5 moles here, you need to have 1 mole of H2F2 for this to fully react. But the fact that we don't have 1 mole, we only have 0.5 moles, tells us we don't have enough H2F2 for this reaction to happen. We need to have 1 mole. We just calculated that because of the ratio, but we calculated that in 20 grams, there's only 0.5 moles. We don't have enough. Therefore, H2F2 is the limiting reactant and SiO2 is the excess reactant. Okay. Yes, this is the hardest topic in moles, I would say. Yes, it is. So the hardest type of question you can get. Again, if you want to practice this, go on our website. We've got questions on this as well. Okay, so we're going to jump now to topic 5. Topic 5, okay? And this is the triple stuff. We'll do this at the end. Let's jump to topic 5, guys. Topic 4, I'm going to leave to the end. Topic 5 is relatively short. This is all to do with energy changes. Half equations will come in the last session. That's topic 4. Yeah. Percentage yield. Yes. Triple, guys. That's only triple. So we will do percentage changes, atom economy, concentration of solutions, and titrations. We're barely going to get a break for triple, guys. I'm just warning you now. Barely going to get a break for this next part. So first thing we're going to look at is endothermic and exothermic reactions. Thankfully, topic 5 is the shortest topic in chemistry. In order to remember the differences between exothermic and endothermic reactions, you can use Mexobendo. I'll talk about the M and the B in a second, but let's look at the others. So in exothermic reactions, energy exits. So exothermic reactions are reactions where energy is lost from the reaction. Endothermic, we've got an EN here for enters. Energy enters. So endothermic reactions are reactions where energy is taken in from the surroundings. We've covered this already in biology. Remember, photosynthesis was endothermic, respiration was exothermic. Endothermic reactions are reactions where the temperature goes down, DO for down. Temperature decreases in an endothermic reaction. So you can use that to help you remember that, which means the opposite happens in exothermic, the temperature increases. Examples of exothermic reactions that you need to know. We have neutralization, which we're going to talk about in the last topic. We have combustion. That's when you burn a fuel, when you react something with oxygen. And we have oxidation reactions as well. All of those are examples of exothermic reactions. Practical uses, these are 2 that are stated in the spec. We've got hand warmers and self-heating cans. Just memorize those. They'll ask you, they're like stating questions. So they're very easy to answer. Endothermic reactions, like I said, they take in energy, they absorb energy. There's a decrease in temperature. Examples of this, again, this is in the spec, citric acid and sodium hydrogen carbonate. You just need to recall that example. And thermal decomposition, that's when you get something and you heat it up and it breaks down. Will we go back to concentration? Yes, we will. Don't worry. We'll go back to that for triple, guys. Oh, wait. Triple. Let me quickly look back at this. Actually, sorry, I keep switching. This was triple only. I think there was just an equation I needed to tell you guys for concentration for combined, guys. Sorry, an equation for concentration. I should tell you. Concentration is equal to mass over volume. You can get questions on concentration if you're combined as well. So mass is measured in grams, volume is measured in not centimeters cubed, it's measured in dm cubed. Concentration is measured in grams per dm cubed. Sorry guys, I missed that one out. dm cubed, does anyone know how to convert from centimeters cubed to dm cubed? Because you need to do this quite a lot in your calculations. How do you convert from centimeters cubed to dm cubed and vice versa? Can mass also be relative atomic mass? No. Only if you have 1 mole of it, it can be the same. So, yes, to go from centimeters cubed to dm cubed, you want to divide by 1,000. dm cubed back to centimeters cubed, you want to times by 1,000. Well done, guys. All right, so just be able to use that equation as well. All right, let me go back to topic 5 again. Sorry. Practical uses of endothermic reactions are sports injury packs. They're like ice packs, but they don't use ice. They just have a chemical reaction in them which absorbs energy, so it makes them feel cold, and you apply that to like your injuries, and it makes you feel better. Required practical. I can't believe we haven't seen a single required practical in chemistry paper 1 until now. This is the first one that we're coming across. It's investigating energy changes, okay? So what you do here is you have a reaction and you measure the temperature change, and from that you can tell how much energy is being released, all right? So for this, the steps here, you can memorize the steps here. I've got a memory trick here for this. So let's talk about the points real quick. So the larger the temperature change, the larger the energy transferred. So what we're going to do is we're going to get a polystyrene cup, and we're going to use Vitsha to remember all the steps. Okay, so Vitsha. So first thing is the V. The V is for volume, because we need to measure the volume of whatever acid it is you're reacting using a measuring cylinder. When you're writing these, if it was a 6 marker, you have to always state the equipment that you're using. All right. So what we're doing is we're trying to react 2 things. Let's say we're reacting hydrochloric acid and sodium hydroxide. We need to measure the volumes of both of those, and we want to put it in a polystyrene cup. Okay. Why do we use a polystyrene cup? Because it insulates. Remember, this whole experiment is all about energy changes, it's temperature changes. You don't want to use a beaker because that's made of glass and it's going to lose heat to the surroundings. So your temperature change is not going to be very accurate if you use something like glass. So you want insulation. So you can mention for that polystyrene cup. That'll get your mark. With a lid. That will also reduce how much heat that's lost to the surroundings. Then we've got temperature. So at this point, you want to measure your temperature using your thermometer. You want to measure the initial temperature. And remember to state what equipment you're using. So measure initial temperature using a thermometer. So your reaction has just started in your polystyrene cup. the temperature's rising. Remember, it's neutralization. It's exothermic. It's getting hotter and hotter and hotter and hotter. The temperature's rising. You want to make sure the whole thing is reacting properly, so you stir it. Yeah, not much to say about stirring. Stir it with the thermometer sometimes makes it easier. Then you note down the temperature that's the highest. So the temperature will keep rising, 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 and then you note the highest temperature. Because what will happen is the temperature will rise and then it'll start falling again. And loads of people make the mistake of giving the final temperature, which isn't good because by that point, the reaction's finished. The reaction finishes when it reaches its maximum temperature. So that's why we need to record the highest temperature. And then you repeat. That's what the again is for. So you repeat with different volumes of acid and alkali. And the one with the highest temperature change is the one with the biggest energy change. So use VITCHA. If you get a 6 marker asking you to work out this, to explain this practical, just use VITCHA and you'll get all 6 marks. It's come up in the past before. Why is the temperature rising? Because it's exothermic. It's exothermic, meaning it's going to get hotter. You want to see how much it's getting hotter by, because the more it gets hotter, the bigger the energy change. Is titration paper 2? For AQA, it's paper 1. So we're going to go through that for triple students at the end of this one. Okay, next we have reaction profiles. So reaction profiles basically tell you how energy changes during a reaction. So you have energy on the y-axis and you have progress of reaction on the x-axis. This tells you how energy changes as the reaction goes on. You have the reactants at the very beginning on the left and the products on the right. And to get from the reactants to the products, there's a trend. It goes up and down. The graph goes up and then it goes down. This peak, this little hump here, the height of this hump is called the activation energy. The activation energy, you need to know the definition of this, is the minimum amount of energy that you need for these reactants to react. So these reactants are moving around, they're colliding with each other, and the energy that they need to collide and react to form the products is known as activation energy. And that is always the height from the reactants to the peak of the graph. The other thing you need to be able to label is the energy change, the overall energy change. That's simply the difference between the reactants and the products. All right. So for these reaction profiles, you need to know the difference between an exothermic reaction profile and an endothermic one. So exothermic, the reaction decreases, the energy decreases, goes downwards. And for endothermic, the products are higher than the reactants, so the energy increases overall. But you can see here the activation energy is much lower for the exothermic reaction when compared to the endothermic reaction. Can we use VITCHA for a test for reactivity of metals? No, I don't think that would work. You don't need to temperature change, insulate. Maybe that could work actually. Maybe that could work. You need, okay, for VITCHA, do you actually write the letters? Obviously, don't write the letters in your exams. Write on the side somewhere, but then write it fully using phrases in your exam. Okay, VITCHA is just there to help you remember the steps. So I've got volume. You're not going to just write volume and get a mark. You have to explain, measure the volume using a measuring cylinder. VITCHA is just there to help you remember the steps. Can you use photosynthesis as endothermic? Yes, yes, yes. Okay, cool. Next. Energy changes of reactions. This is bond breaking and bond forming. So every reaction has 2 processes: bond breaking and bond forming, or bond making. Okay. One of these are exothermic. So one of these use energy and one of these release energy. So we've got bond breaking And you can remember that remember when I told you guys about mexobendo right at the beginning? Bond making is exothermic. Bond breaking is endothermic. All right, that's what mexobendo is there for. So any reaction, think about what you're doing. Let's look at the reaction in this example. You have hydrogen reacting with chlorine. So you've got H2, which looks like that. What we need to do first is break all the bonds. Imagine a reactions like this. You have Lego pieces, and what you want to do is you want to break all the Lego pieces into their individual Lego pieces. You have Lego blocks, and then you break them down into individual pieces, and then you rearrange them. That's essentially what a reaction is. So these are your Lego pieces, and you're splitting them up. You're breaking these bonds. That's bond breaking. Mexobendo, bond breaking is endothermic. So this requires energy. Then you get all these 4 pieces and you rearrange them. So now we've got HCl and we've got another HCl there. That's how we got 2 HCl here. That's bond making. So we're breaking all the bonds and then we're making new bonds. Making new bonds is exothermic. Breaking bonds is endothermic. So that's what I'm trying to say here. So in an exothermic reaction, you're basically releasing more energy during bond forming than taking in energy during bond breaking. So when you're breaking a bond, remember, you're taking in energy. But in an exothermic reaction, you're doing less of that. You're releasing more energy. So that's why in an exothermic reaction, your overall, your net energy change is you're releasing energy. Okay. Now, we can use this whole concept for bond energy calculations. So we can work out the energy change of something by working out the bonds broken and minusing out by the bonds formed. And this is a calculation question that you can just practice, guys. All you have to do is count the bonds in the reactants, count the bonds in the products, and subtract them. So it's reactants minus products. So if you get a question like this, calculate the energy change for the reaction between hydrogen and chlorine given the following information. You just need to remember, do reactants minus products. You'll get given a table, and every bond will have an energy change with it. So a HH bond would be 432. So 432 plus 239, that's all of your reactants done, minus all of your products. We have 427 here, but we've got 2 of those. Look how many we've got. We've got 1 here, 1 here. So we got to do 2 times 427. Do all of that, and that will give you your final energy change, minus 183 kilojoules per mole. So you have to always use the same units that you have in your table. We have kilojoules per mole here. And that will give you an exothermic reaction. So if it's negative, it means it's an exothermic reaction. If it's positive, it's an endothermic reaction. Yes, exactly. Okay. Topic 5 done. We've got a triple topic here. Right. Break time. It's going to be slightly longer break because I think triple guys need at least a 5-minute break. And this stuff will probably take about 15 minutes. Let's have a break until 2:40 for combined, guys. Break until 2:40. 2:40. So you guys have a slightly longer break because triple guys, we've got a bit to get through now. So combined, guys, I'll see you at 2:40. Triple guys, we're going to go back to these calculations, back to quantitative chemistry. Gas test paper 2, yes, pretty much. Yes, see you in a bit. Combined, guys, see you in a bit. Triple guys, Well done for staying staying with me here. So, concentrations of solutions. I told everyone equation earlier. Concentration equals mass over volume. Triple people need to know another one. Concentration equals moles over volume. So if you use the mass over volume one, your units for concentration is grams per centimeters cubed. If you use the second equation, it's moles per centimeter, grams per dm cubed. And on this side, it's moles per dm cubed. If you use this equation. So concentration can be measured in both. It depends on the scenario. So look at the question, look at what they give you the units in, and try and use the correct one based on that. Calculate the mass of a solute. So look at this. We've got the mass of sodium chloride present in 23 centimeters cubed of a solution with a concentration of 4.6 grams per dm cube. So it'll be quite clear here that we need to use the first equation, the one with mass in it, mass over volume. You need to convert centimeters cubed into dm cubed. So remember, to do that, you want to divide by 1,000. So 23 divided by 1,000 gives you 0.023. We've rearranged this equation. Concentration is equal to mass over volume. To give you mass is equal to concentration times volume, which will give you 4.6, which is in the question, times by what we just worked out, 0.023, and that gives you 0.1058. And then there's another example here you guys can try with your with moles in it instead of mass. Okay, next thing we're going to look at is reactions between two solutions. So this comes under titrations as well. So we've got a question here under titrations. So what I'm going to do is I'm going to jump to titrations because this covers both things. And I'm going to go through that instead. So this is topic 4. I don't know why they put it in topic 4 because it's technically quantitative chemistry, but they have it in the acids and bases one, which kind of makes sense as well. But let's go through titrations as well. So titrations, you do this for neutralization reactions. So neutralization reaction, we're going to learn in the last part, is a reaction between an acid and an alkali. And in a titration, what you're trying to find is you're trying to find how much acid is needed to neutralize a particular alkali. We haven't done topic 4. No, we're going to do that right at the end. But titration, we're doing now. So that is topic 4 for triple, guys. So setup for titrations. There's a burette. What a burette is good at is good at measuring variable volumes very accurately. It's got a tap at the bottom. You can control how much acid you're adding to an alkali. We have a pipette. A pipette is very good at measuring single volumes very accurately. So if you want to measure 25 centimeters cubed, is much more accurate than using a measuring cylinder. So that's why we use a burette and a pipette. We also need an indicator and a conical flask. These are the 3 different indicators you need to be aware of, guys. So phenolphthalein, methyl orange, litmus as well. You need to know the color in acid and their color in alkali. So memorize these colors, guys. Phenolphthalein is the one that comes up the most. It's colorless in acid and it's pink in alkali. And what you do in this setup, you add your alkali to the acid and you basically wait for the color to change, the color of the indicator to change. So as an example, this is the calculation we're going to practice, the mole calculation we're going to practice. Let's imagine we had sulfuric acid reacting with sodium hydroxide. So we add sulfuric acid in here, we add 25 centimeters cubed of sulfuric acid, H2SO4, and then NaOH, we put that in the burette. You add your indicator into the conical flask as well, and then you open the tap. So all of this alkali is going to flow into this conical flask, and you wait for the color to change. As soon as the color changes, you stop and you close the tap. While this alkali is flowing, remember to swirl your flask to make sure everything's mixing. And also at the end, try and add the alkali drop by drop. Those are things to mention when it comes to answering questions on it. Then you repeat that method. So what you would get is a volume. So once the color has changed, you note down that volume that you just got from the burette, and you repeat that process over and over again. And you have several different titration values. We call them titers. Now, we're going to use this volume to do a mole calculation. The aim of this is to work out the volume and the concentration of sodium hydroxide. So the question is, let's go back to the question. We had, according to our notes, we had 1.3 moles per dm cubed of sulfuric acid, and it was reacting with sodium hydroxide with an unknown concentration. We used 25 centimeters cubed of sulfuric acid. So let's note these numbers down. So 1.3 for sulfuric acid. I'm going to put 1.3. That's the concentration. And the volume is equal to 25 centimeters cubed. Okay, I've done that here actually. Now, the volume for sodium hydroxide, we work out using our titration values, our volume. We want an average of these. But for titrations, you don't use all the values. You have to use concordant results. Those are results which are within 0.1 centimeters cubed of each other. So we would basically ignore this top value. All the other four are all good, but the top one is usually the top one you ignore, sometimes another one. Because it's too far off, it's not within 0.1 of the others, we completely ignore it. And we work out the average of the other four. When you work out the average, you get an answer of 23.5 centimeters cubed. So we're going to now use this in our mole calculation here. So remember I said always mark your known and your unknown. We're going to use CRU here again. So remember there's 3 stages here. CRU, first thing is to work out the known. Our known is the sulfuric acid. We want to work out the moles of the known. So we're going to use the equation that I told you about. Concentration is equal to moles over volume, but we're going to rearrange that to give us moles equals concentration times volume. What you need to remember here is that in these equations, volume needs to be in dm cubed. Our volume is in centimeters cubed. We need to convert that. So we need to divide by 1,000. So if you get 25 centimeters cubed, so let's get this 25 centimeters cubed and divide it by 1,000, that gives us 0.025 dm cubed. So we can do 1.3 times 0.025 to give us the moles. And that gives us this. That's the first step done, CRU. Second step is ratio step, R. So now we look at the ratio. We've got a 1 in front of the H2SO4. We've got a 2 in front of the NaOH. So the ratio is 1 to 2. In the previous step, we had 0.0325 moles. So we need to multiply this by 2 to give us 0.065 moles. That's our moles of NaOH. And that can lead us to our final stage in CRU, which is U. Find the unknown. We use the same equation again, moles over volume. So we use the 0.065 we just calculated, but we divide it by the volume that we got from the titration. Remember that average that we worked out? Remember to convert it into dm cubed first and put that into the equation. Divide the 2 and you get 2.77 moles per dm cubed. That is a typical calculation for titration, guys. and that covers your moles as well. Okay, I will try. It does. I will try and give you guys a break, but let's see how it goes. Let's see how everything goes. I'm jumping back to topic 3 now, guys. Other things you need to be able to do is you need to be able to convert. Remember those 2 units for concentration I gave you, moles per dm cubed and grams per dm cubed. You need to be able to convert between the 2. So grams per dm cubed to moles per dm cubed, you need to divide by the MR of whatever it is that you're working out. And the other way, you times by MR. Okay, and we've got an example here that you guys can try. Next. Volume of gases. Volume of gases. This is another equation you guys need to be aware of. 1 mole of any gas always takes up the same volume. It always takes up 24 dm cubed. You need to remember that. If the room temperature and pressure is standard, so in a normal room, a gas will always take up 24 dm cubed if there's 1 mole of it. You can do calculations with this as well. We've got an example here where we use the formula to work out how much volume 218 grams of oxygen gas will produce. First thing you need to do is work out the moles using mass over MR. Once you've worked out the moles, you can put it into this equation. You can rearrange it and do the moles times 24, and it gives you 163.5 dm cubed. If they give you a question like this, calculate the volume of ammonia formed when 38 dm cubed of nitrogen reacts with hydrogen. It's very easy. So if we have 38 dm cubed here, you literally just do the ratio step. All you have to do is the ratio step. You can only do this if it's the volume equation that you're using. So this is a volume that they've given you, and they ask you for the volume of something else. If they give you the volume of a gas and they ask you to find the volume of another gas and they give you the reaction, just use the ratio of the moles. So that would mean this is a 1:2 ratio. So you just multiply this by 2 to give you 76. If they asked you how much hydrogen there is, it's a 1:3 ratio. So you multiply it by 3. Okay, that's all you need to do. Okay. Haber process. Yes, that's right. Percentage yield. Someone was asking about percentage yield and atom economy. Here we go. Yield. The word yield, what does that mean? Yield in chemistry means the amount of product that you have. Okay. So here we have a reaction. I've given you the mass of the reactants and the product. So the yield here is whatever the product is 16.2 grams. You can have 2 different types of yield. You can have theoretical yield and actual yield. Theoretical yield is the yield you get when you do a calculation. So when you do a mole calculation, you get the theoretical yield out of it whenever you work out the mass of something. That is like the maximum amount of mass that you should be getting from a reaction, ideally, if the reaction went perfectly. But the thing is, reactions don't go perfectly. So if you were to do a reaction in real life, you would find that the yield is smaller than the theoretical yield. That's called the actual yield. So actual yield is the one that's produced from the experiment when you physically do it in a lab. Theoretical yield is the one that you calculate. It's the product that you calculate. That's the amount that should be formed. You can work out percentage yield by dividing the 2 and timesing by 100. So we've got an example here. We've got 15.3 grams of copper carried out in the following reaction, and they've told us the mass of copper oxide. That is something you can ignore until the very end of the calculation. So the calculation that you're trying to do is you're basically taking this as your known and the copper oxide as your unknown. I've done that here. You're basically doing a normal mole calculation using CRU, and then you're adding a step at the end of it. People get confused by percentage yield, but it's essentially just a normal mole calculation with an extra step. So imagine that was unknown and our unknown. What would we do? We would find out the moles of the known first. So 15.3 divided by 63.5 gives us the mole. Then we do the ratio step. The ratio is 2 to 2, which is basically 1 to 1. So if we got 0.24 in that first step, that means we have 0.24 of copper oxide. And then the final step is CRU, is find the unknown. We do moles times MR, which is what we did here. That gives us a mass of 19.1 grams. This is our theoretical yield. Remember I told you this is the one that gets formed from reactions, from our calculations of reactions. What we want to do is now actual yield over theoretical yield. But what's our actual yield? We have to go back to our question. Remember I told you to ignore this until the very end? Now is the time to use it, because this is the actual yield. This is what they have told us has been formed from this reaction. That will always be given to you in the reaction, the actual yield. So we do the 18.3 divided by theoretical yield that we just calculated, and we get a percentage after you've multiplied that by 100. Theoretical yield is always higher than actual yield. Yes, it is. Yes, it is. So you always want percentage yield to be as high as possible. It can never be 100% because things can happen. Why is it never 100%? Because when you do a reaction for real life, in real life, you could lose some product. Like when you're transferring something from one container to another, you could lose a few atoms. There could be side reactions. One of your reactants could be reacting with something else that you don't mean it to react with. And you might have reversible reactions, a reaction that goes back to its original reactants rather than going to the products. Then we've got atom economy. Atom economy. This is a bit easier to work out, in my opinion, because it's just MR calculations. So they'll say, find the atom economy of something in something. So find the atom economy of potassium chloride in this equation. Okay, so what you want to do is you want to work out the MR of the desired product, that's whatever they ask you in the reaction, potassium chloride, over all the reactants. But I like to do this, guys, because I just wrote this because this is what's written in your spec. I would rather do all products, because you're doing two calculations using the same thing. So look at this. You find your desired product. So that's potassium chloride. You find the MR of potassium chloride. Look, I'm going to get the same answer as the one in this example. So potassium chloride is 39 plus 35.5. And you'd multiply it by how many potassium chlorides there are. There are 2. And you divide that by all products. The reason it makes it easier is because you're doing the same calculation twice, because now we're doing everything in the green box. We're doing 2 potassium chlorides again. So I'm going to do that same calculation again. 39 plus 35.5 times by 2 at the bottom. And we're only adding one extra thing in it, which is the bromine. Bromine is 80. So we're going to add 80, but 2 lots of 80. And then we get this whole calculation and multiply it by 100. And you should get your percentage yield. If you guys want to try that out, you would get the same percentage yield of 48.2. It can never be 100%. No, percentage yield can never be 100%. Atom economy can be 100%. Can someone tell me, how can atom economy be 100%? When do you multiply the number in front of the element? Okay, so remember in mole calculations, I said never multiply by the number in front. The only time you multiply by the number in front is when you're doing an atom economy calculation. Okay? All other times, you only use this in the ratio step. By an atom economy, there's no ratio step. You don't use this in mole calculations, but in atom economy, you use the big numbers. Exactly. Well done, guys. When one product is made, you have 100% atom economy. Percentage yield is impossible to get 100%. It's always going to at least be 99%. Okay, 5-minute break, guys. 5-minute break. And we'll do the final topic. We'll be back at 2:40. I'm just going to get a drink of water and be back. Ready? Okay, I'll see you guys in a bit. Welcome back, guys. Last bit on a scale of 0 to 10, guys. How fried are your brains? It's a lot of information. I know some of you might be confused. I'm hoping when you look back at this, it'll make sense. I was going through stuff. There's a lot of content in chemistry, guys. 10. Last stretch. Come on, guys. Let's push to the end. Let's push to the end. We've got acids and alkalis to go through, which is hopefully a bit more straightforward. Electrolysis is not, but I'm saving it to the end. We will probably overrun if I'm going to go through electrolysis properly, guys. I want you guys to understand it because it's the trickiest topic, and I'll leave that open for questions at the end as well. If you have any questions on any of the stuff we went through before as well, let me know, and I'll answer all those questions. And obviously, we've got the wheel spin as well at the end. Yes, thank you for reminding me. It was topic 3 that fried me. Sorry to hear that, Sabi. That's the one that people struggle with them. No, they don't struggle that with the most, but that's the one you got to practice the most. It's yeah, you got to do a lot of questions because it's calculations based. Now, topic 4 is what we're going through now. Yes, I'll go through fuel cells as well. Don't you worry. Don't you worry. Let's start off with reactivity series first. Okay. This is the reactivity series. There might be extra ones that you guys know of, like loads of people know about gold underneath. There's gold, silver is just above gold. So at the top, we have the most reactive and the least reactive is copper. This is what it says in the AQA spec. But just be aware that below copper, we have silver and gold as well. We also have these 2 non-metals. This is useful for electrolysis. This is useful for metal extraction, which is what we're going to look at next. So you need to know that when you have a more reactive element, the reactions are more violent. And you can see that here. So I've got this table here that you guys can look at later. And you can see higher up, the reactions are much more violent. Lower down, there's almost no reaction going there. You need to be able to see that and explain that in a question. Okay, we got some memory tricks here for the order of the elements in the reactivity series. If you react a metal with water, you can have a hydroxide being formed. So this first one we've seen already. Group 1, very first topic. We did group 1 with water, it forms a metal hydroxide. But note here that for group 1, the metal hydroxide that's formed only has a single OH. For group 2, it has 2 lots of OH. Yeah, that's the only difference. If you were asked to write the word equation, it's straightforward. It would be potassium plus water forms potassium hydroxide plus hydrogen, or calcium plus water forms calcium hydroxide plus hydrogen. Okay. When you react a metal with an acid, it will form a salt and hydrogen instead. So if you have hydrochloric acid, it will form a chloride. I'm going to show you what the other acids form as well in a bit. So iron plus hydrochloric acid forms iron chloride plus hydrogen. MASH, yes. Frozen, thank you. You mentioned that in our FRL class as well, didn't you? Metal plus acid forms salt plus hydrogen. Thank you for remembering that one. So metal extraction. So when we want metals for like our everyday use, we use them in like what, bridges, cars, loads of different appliances. We use metals, right? Where do we get those metals from? We can't just find pure metals in nature. But there's a few you can, but there's not many that you can find in nature just as a metal on the ground. They're usually in the form of metal oxides. That's because metals usually react with oxygen to form metal oxides. we dig up these metal oxides. They're called ores, O-R-E-S. We dig these ores up, and the aim is, once we dig these ores up, we need to get rid of the oxide. We want to get rid of the oxygen. This reaction is called reduction. So reduction is the process of removing removing oxygen. So reduction is the loss of oxygen. The opposite of reduction is oxidation. That's the gain of oxygen. So to extract a metal, we where is it? Oh, sorry. Some examples of oxidation. Here we go. Copper plus oxygen. The oxygen is being added to copper to form copper oxide. Oxygen is gained by copper. So we say this is an oxidation reaction. Here's an example of a reduction reaction. Copper oxide plus carbon forms copper plus carbon dioxide. The oxygen is being removed and it's going to the carbon. So the copper is being reduced. The carbon is being oxidized because copper oxide is losing oxygen to form copper. Carbon is gaining oxygen to form carbon dioxide. We call this a redox reaction because oxygen and reduction is happening at the same time. So we use this to extract metals. The ideal way for us to extract metals is to use reduction. So what we do is we get the ore, so copper oxide, for example, and we react it with carbon. And what will happen is the copper oxide will be reduced. It will lose its oxygen and it will go to carbon because carbon gets oxidized. And what will get formed is the pure metal, so pure copper, and carbon dioxide. So we try to use this to extract normal metals. But the problem with this is that it only works if copper is more reactive, than the metal itself. So if we look at our reactivity series, this is why I had carbon here. Only these metals can be extracted using carbon because carbon will take the oxygen away from the ores. Anything that's above carbon in the reactivity series, we can't extract using reduction. For this, we need something more powerful. Because the carbon is not going to take the oxygen away, we have to use another process, which is called electrolysis. So the whole electrolysis process we'll go through in a bit. But for now, just know we use electrolysis for metals which are more reactive than carbon. There are some metals where we don't need any extraction process. So like gold, for example, we just go to a cave and we mine it and we've got pure gold. But that's only for ones which are really, really unreactive. But most of the cases in exams, they're going to be either reduction with carbon or electrolysis. It is pre-recorded. You'll be able to watch the recording and you'll be able to rewind as well. Go to the back. Is this a displacement reaction? Yes, it is also a displacement reaction. Yeah. Okay, so redox reactions. I said already, redox reaction is a reaction where oxidation and reduction happens in the same reaction. And remember I said oxidation is the gain of oxygen, reduction is the loss of oxygen. There's two ways you can describe oxidation and reduction. So in terms of electrons, you can use oil rig. Oxidation is the loss of electrons. Reduction is the gain of electrons. If you do it in terms of oxygen, it's the other way around. Oxidation is the gain of oxygen. Reduction is the loss of oxygen. So just make sure you know when to use which one. It all depends on whether you're talking about electrons or oxygen. Two different definitions. That's why oil rig doesn't always work. So displacement reactions. We've already talked about displacement reactions when we talked about group 7. Remember, that's when a more reactive element replaces something that's less reactive. So zinc plus copper sulfate turns into zinc sulfate plus copper. This is where a more reactive element, so the zinc is replacing the copper in the compound. This is an example of a redox reaction. And I can show you why here. This is the symbol equation for that. Zinc plus copper sulfate forms zinc sulfate plus copper. What we're going to do now is going to write something called an ionic equation. So in an ionic equation, you break things up into their ions, if they're ionic. So zinc here isn't an ion. We keep it as it is. Copper sulfate is made up of two different ions. It's made up of Cu2 plus ions and SO4 2 minus sulfate ions. Zinc sulfate is made up of Zn2 plus ions and SO4 2 minus ions. Copper is just an element. We just keep it as it is. So what we do is we basically get this ionic equation, and from there we can figure out what's being oxidized and what's being reduced. So look at this here. Zinc is going from Zn with no charge to Zn2 plus. How do you go from a Zn atom to an Zn2 plus ions? To get a positive ion, if you guys remember back to our first session, you have to lose electrons, right? Electrons are lost. If electrons are lost, it means you have an oxidation reaction. We can do the same for copper. Copper is going from Cu2 plus to Cu. If you're going from a positive to a neutral atom, you need to gain electrons. Gaining electrons is reduction. So this is a reduction reaction. Therefore, we have reduction going on here and we have oxidation going on here in the same equation. Therefore, we can call this a redox reaction. So we said Cu2 plus is going to form Cu. How do you get Cu2 plus to Cu? You need to add 2 electrons. So imagine having a copper ion with a 2 plus charge. If you add 2 electrons to it, it becomes a copper atom. So we can show electrons in an equation by using E minus. And we call this a half equation. So this whole thing here is a half equation. For Zn, for zinc, we're doing the opposite. To go from Zn to Zn2 plus, you need to lose electrons. So to lose electrons, you put electrons on the right-hand side. So we put 2 electrons here. If you get a Zn atom, imagine getting a Zn atom and taking 2 electrons away from it, you get Zn2 plus. This is another half equation here. Putting those 2 half equations there gives us the full ionic equation. We're going to see half equations again when we do electrolysis. What is in reduction, the electron is located on the left, and oxidation, the electron is located on the right. Yes, that's a good way of thinking of it. How do you know which side of the equation they go on the half equation? Is oxidation always the one on the left? Yes, it is, because the electron goes on the right in oxidation because it's losing electrons. In reduction, the electrons always go on the left because they're being added on. Are the grade boundaries low? You don't know the grade boundaries until the exams have actually been done. So they give you the exams, they let people do it, and then they base the grade boundaries on after that. There's no, you don't know what happens to the grade boundaries. It all depends on how hard the exam is. Can you show half equation with diatomic? Yeah, we'll do half equations in a bit, guys, when we do electrolysis. Let's quickly go through acids and bases now. So pH scale and neutralization. So pH, this is a slightly easier topic. It tells you how acid or alkali something is. All right. It's a scale. You can tell how acid or alkali something is by using the pH scale, which goes from 0 to 14. So if something is 0, it is very acidic. If it's 14, it's very alkali. If it's 7, it is neutral. An acid, definition of acid, is something that releases H plus ions. Alkalis are something that release OH minus ions. You can tell whether a solution is acidic or alkali by adding an indicator. So universal indicator is a very common one. And the color will tell you how acidic something is. So if it's red, you can say it's very acidic. If it's orangey yellow, slightly acidic, green, neutral, blue, slightly alkali, and purple, very alkali. So you can predict roughly what pH something is, but you can't tell exactly what pH it is. In order to find out what the exact pH of a solution is, you have to use a pH probe and pH meter. So these are these little probes that you put into the solution, and it gives you a number. It gives you a digital value, and that tells you the actual pH. So it's much less subjective to using an indicator, because an indicator, you need to judge the color, you need to decide whether it's orange or red, how orange it is, how yellow it is, and it's not very accurate. But this will actually give you a number, so it's much more precise. Yes, you can with purple cabbage. Yeah. Okay. Next up, neutralization. So it's a type of reaction. So a reaction where an acid reacts with an alkali to form salt plus water when you react those two. Any reaction between an acid and an alkali is a reaction between, remember I said H plus for acid and OH minus for alkali. So when those two react, you get water being formed. This is known as an ionic equation for a neutralization reaction. Any neutralization reaction always has this ionic equation. Acid plus alkali goes to form water, but we're just using the H plus and the OH minus ions here. So remember this equation here. And note down that these are also aqueous. These are two solutions, and you're reacting them together to form liquids. Okay. Different types of acids you can have. So what do acids do? When you put them into a solution, what you'll notice is that every acid that you've come across has a H in it. Hydrochloric acid is HCl. Nitric acid is HNO3. Sulfuric acid is H2SO4. They always have a H in them. Remember, that's because they release H plus ions in solution. So when you add them to the solution, they do something called dissociating or ionizing. These acids ionize in water. When they ionize, what they're doing is they're breaking down into their ions. So HCl turns into H plus and Cl minus ions. Nitric acid breaks up into H plus and NO3 minus ions. And sulfuric acid breaks up into H plus ions and SO4 minus ions. They are dissociating, they're ionizing. And every time they're releasing these H plus ions. These H plus ions are what make it acidic. The more H plus ions you have, the more acidic it is. You need to know the difference between a strong and a weak acid. Definition of a strong acid is an acid that fully ionizes in water. Fully ionizes means every molecule of acid you have breaks up into its ions. So if you had a beaker of 1000 HCl molecules, all 1000 will break up into H plus and Cl minus ions. You don't have anything else in there. That's what fully ionizing means. So that means you have 1000 H plus ions. That's going to make it very, very acidic. That's a strong acid. If you have a weak acid, that's not what happens. Imagine you had 1000 acid molecules of a weak acid. They only partially ionize. So that means only, I don't know, maybe 100 of 1000 break up into their ions. So you're left with loads of molecules that haven't broken up. So you've only released about 100 H plus ions. If that's the case, it's not going to be very acidic. It's going to be slightly higher pH. Yeah. Yep. Well done, Safa. So definition of a strong acid, fully ionized. Their pHs are lower. They're more acidic. Weak acids, partially ionized. Only some of the acid molecules are broken down. So that means there's lower concentration of H plus ions. So that means the pH is slightly higher. It's less acidic. You need to be able to do calculations using this. So the relationship here, it's a bit confusing. If you have a H plus concentration, so this is how much H plus you have in an acid, and you increase it by 10, the pH will go down by 1. That's the rule. If you decrease it by 10, the pH will go up by 1. So here we got a question here. We have a solution of hydrochloric acid, and it was diluted until its concentration decreased by 100. So if the concentration decreases by 100, it means the pH will go up by 2. So the question says, what is the change in pH? The pH will increase by 2. So that's why I made this diagram here, just to help you guys out on figuring out the pH. So they could give you like a starting pH and ask you to find out the final pH of something. So let's say we had a pH of 3, and an acid had a pH of 3, and it had a concentration of 0.1 mole per dm cubed. Yeah, just as an example. And they diluted this to make it 0.01 mole per dm cubed. So they made it 10 times smaller. They basically divided it by 10, right? They've gone up a step here. If that's the case, that means your pH goes up by 1. So what would the new pH be, guys? What would the pH be? 1 order of magnitude is times 10, so the change in pH is 1 order of magnitude. It's 4, exactly. It goes up by 1. If we increased it by a factor of 10, if we made it 1 mole per dm cubed, then it will go down by 1. It will go to a pH of 2, and so on. So if it increased to decreased to 0.001 mole per dm cubed, then it will go up by 2. So it will go to 5, a pH of 5. That's the rule. Okay? Well done, guy. Do we need to know acid dissociation constants? No, not at all. That's a A-level thing. You don't need to know that. Don't forget the wheel. I won't forget the wheel. Don't worry. Okay. And this last bit here is just to tell you the difference between acid strength and concentration. So remember, strong acid fully ionizes. Weak acid partially ionizes. A concentrated acid, think back to your definition for concentration. It means you have a lot of acid in a given volume. You have a high amount of acid in a given volume. A dilute acid, you have a low amount of acid in a given volume. They mean different things. So you can have a strong acid with a dilute concentration. You can also have a weak acid with a high concentration. So make sure you know the difference between these two things. It's right here on this page. Okay. What is the wheel? The wheel is something that we're going to spin. So for everyone who wants the free paper 2s, and one person's going to win it. We're going to spin the wheel, and whoever it lands on will get the paper 2 classes for free, and also the cram classes for free as well. Reactions of acids. So I've told you guys already, acids, different acids forms different salts. So hydrochloric acid forms chlorides, nitric acid forms nitrates, sulfuric acid forms sulfate. And you need to be able to write an equation for any acid and any base. A base is basically something that reacts with an acid. So if you have an acid reacting with a metal oxide, it forms salt plus water. Hydrochloric acid plus calcium oxide, for example, we form calcium chloride, because remember, hydrochloric acid always forms a chloride salt. So it forms calcium chloride plus water. So the hard bit here is figuring out the salt. You just use the metal, and then you look at the type of acid it is, and then you can work out what the salt is. If you had an acid plus a hydroxide, it would also form a salt plus water. So nitric acid plus sodium hydroxide will form, you get the sodium. You've got nitric. If you look back at that table, that forms a nitrate. So that's going to form sodium nitrate plus water. Then for carbonate, this is the only one that's different. Acid plus a metal carbonate forms salt plus water, but also forms carbon dioxide. So if we had sulfuric acid plus calcium carbonate, that will form calcium sulfate plus water plus carbon dioxide. So the only different one there is the carbon dioxide. Okay. Next one. Required practical, making salts. So this is the crystallization one that we talked about earlier. So in this practical, you basically need to be able to figure out what type of salt is being made. So if you have a practical asking you to make a lithium chloride salt, let's say we have a practical asking you to make a lithium chloride salt, they will ask you what acid needs to be reacted and what base needs to be reacted. So from that table I told you earlier, you need to use hydrochloric acid. I hope you guys remember that. If you want to form a chloride, you use hydrochloric acid. If you want it to be lithium chloride, you need lithium something. You need either lithium oxide or lithium hydroxide or lithium carbonate. Usually they only ask you insoluble bases, so they'll ask for lithium oxide and lithium carbonate. And you need a series of steps here to explain how you're going to make dry crystals of this. Memory trick here that I've got is HEFEC. HEFEC. What do you guys think the steps are here? We got HEFEC. If you get a 6 marker asking you to describe how to make pure crystals of lithium chloride, what would you say? What would you say? So the H is for heat. What we do is we basically add the lithium oxide to the hydrochloric acid and heat it. Let's write that down. So add lithium oxide to hydrochloric acid and heat. So the reaction will take place. What you also need to do is you need to make sure that the solid is in excess. Do you guys remember what excess means? Excess means you have, yes, well done, Katie. You basically need to add more than is enough. So you need to keep adding lithium oxide to the beaker until it's left over. So imagine you have a beaker, you have hydrochloric acid in it, you get a spatula of lithium oxide, and you keep adding it. What's going to happen is the lithium oxide is going to keep reacting, but eventually all of the acid is going to have reacted, and you add the lithium oxide and it'll stop reacting. At that point, it has it's fully reacted, the acid's fully reacted, and you have excess. So you need to do that until it's in excess. Next thing, you want to remove all of that excess. You have extra lithium oxide that hasn't reacted. You want to get rid of it. So you get rid of it using filtering. So you filter it. Then after that, we've got the step here. You go filter, and you basically need to get the solution that you had, the filtrate, and you need to remove as much water as you can from it. You need to basically do crystallization. So you need to evaporate the water until you get crystals, and then you leave it to cool and dry. There you go. That's how you get the 6 marks there. With filter paper, yes. Yes. Do you use a water bath? Yeah, you can use a water bath. Water baths are better. You can control the temperature of that. And then, yeah, at the end of it, you'll get crystals. Cool and pat. Yes. Okay. Required practicals. Yeah, I think there's only 2. I think there's only 2 that we've done. This one is for trip only. We've covered this already. Titrations. Skip. And we're on to electrolysis now. Get ready, guys. Electrolysis is a chemical process. So remember I said you can separate mixtures using physical methods. Compounds, you can use chemical methods. So electrolysis separates ionic compounds. So I hope you guys remember what ionic compounds are. Remember, they're combinations of metals and non-metals. The setup looks like this. You've got a battery, some sort of power source. You've got 2 electrodes that you put into the solution. And then you've got a liquid here, an electrolyte. We call that an electrolyte. This liquid, this electrolyte is literally the ionic compound that you're trying to separate. All right. This ionic compound has to be either molten or aqueous. And I hope you guys remember why. We talked about this in the second session, bonding. Remember, in order for something to conduct electricity, something ionic to conduct electricity, it needs to be molten or aqueous so that someone fell into the trap there. It's not electrons. Remember, electrons, delocalized electrons, it's in graphite and it's in metals. That's why it conducts electricity. For ionic compounds, it's ions that are free to move. Ions. Please remember that, guys. I see this mistake all the time. I'm hoping if I say it enough, you guys will remember in the exam and you won't make that mistake. So let me say that again. Ionic compounds conduct electricity because there are free moving ions. Metals, graphite, graphene, all of those conduct electricity because there are delocalized electrons. Okay, both different things. If you mismatch them, you're going to get the questions wrong. So just be careful with that. So we've got that explanation here. They conduct electricity because the ions are free to move. Because when they're solid, the ions are not free to move. Electrodes, 2 types of electrodes you can have, anodes and cathodes. And what you do is you put these electrodes in, you turn on the current, and it's going to separate the electrolyte, the ionic compound in the electrolyte. And what will happen here at the cathode? So the cathode is the negative electrode. The anode is the positive electrode. So when you switch it on, the negative electrode is going to attract the positive ions in the electrolyte. The positive ions will gain electrons and reduction will occur. What these are always trying to do is form atoms. So positive ions will gain electrons to form atoms. At the anode, negative ions lose electrons to form atoms. So you're always going from an ion to an atom in electrolysis, ion to atom, ion to atom. But at the cathode, reduction occurs, and at the anode, oxidation occurs. Okay, we've got two memory tricks here you guys can use. So oil rig, this is the one that we've already covered. Oxidation is the loss of electrons. Reduction is the gain of electrons. Then we've got another one that you guys have probably not heard of. I made this one up. It's not great, but it works. ORAC, that reminds you that oxidation occurs at the anode. It always occurs at the anode. Reduction occurs at the cathode. So that helps you remember that when the ion goes to the anode, oxidation occurs. It loses electrons. But at the cathode, the opposite happens. Okay? An ox red cat. Ooh, Athena, I like that. That's another way to remember it. Okay. People losing focus here. I know it's been a long day. Okay. So remember the two different types of electrolytes you can have, molten and aqueous. All right. Molten, you're getting the ionic compound, you're melting it to liquid. That's it. Aqueous, you're dissolving it in water. Both of these have separate, slightly different methods to them. The easier ones are molten ones. Reason why is because in a molten electrolyte, whatever the electrolyte is, it will always form the elements within it. Sodium chloride, which is molten, will always form sodium and chlorine. This is not the case for aqueous electrolytes. It's a bit more complicated for that. But if it's molten and you know the name of the electrolyte, you can instantly find out what's going to get formed. So sodium chloride, sodium and chlorine. If it was potassium fluoride, you'd say potassium and fluorine will get formed. If it's calcium oxide, calcium and oxygen will be formed. Straightforward. But that's only the case for molten. They will tell you in the question whether it's molten or not. So this is what happens. Imagine you have molten sodium chloride. In your electrolyte, you've got sodium ions just floating around there and chloride ions floating around. When you turn the electricity on, the positive electrode, the anode, will attract the negative ions, the anions. They all go towards this because they're oppositely charged. They're attracted to them. The positive ions will go to the negative electrode. And remember what happens. ORAC. So at the anode, oxidation will occur and reduction will occur at the cathode. So let's talk about each of these individually. Let's first talk about what happens at what we do first. At the anode. All right. This is the memory trick I like to use for half equations, guys. Okay. Is I am babe. I am babe. And you write it down vertically like this. Okay. So I start off with writing the ions, then write the atoms. M, check if the molecules are diatomic. Then we've got Ba to balance atoms. And then Be for balancing electrons. This is the steps that I want you guys to use when you're trying to write a half equation. All right, so we're going to use this for chlorine. I'm going to do it here. So first start with writing the chlorine ion. What's a chlorine ion? It is Cl minus. You write that on the left. Then you write the chlorine atom on the right, Cl. That's the first step done, second step done. Third step, check whether chlorine is diatomic. What do you guys think? Is chlorine diatomic? Do we need to put a 2 there? Is it ion bay? Yes, you can use ion bay as well. Ion bay just means you just write electrons at the end there. You can use ion bay, ion bay. They both work the same. Yes, it is. Do you guys know all the diatomic elements? All the elements that have a 2 in front of it. Diatomic elements are anything with a gen at the end of it. So we got hydrogen, H2. We have nitrogen, O2, oxygen. All of these end in gen. And halogens, Cl2, F2, Br2, I2. All of these are halogens. They end in gen as well. Those are all. Yes, you guys got it. Okay, so back to the steps. We have written the ion, we've written the atom, we've written the fact that it's a diatomic, the chlorine is diatomic. Next, balance the atoms. Are these balanced? Do we need to put a number in front of either of these? In either of the Cl- or the Cl2? Do we need to put something in front? Halogens don't end in gin, but the word halogen does. Halogen does. Yes, Frozen knows. In front of Cl-, we need a 2. Yes, we have 2 on the right. That means we need 2 on the left as well. The final thing is to balance electrons. Do we need to put these electrons on the left or on the right for this to work, for this equation to work? Is it on the left though? I don't think so. I think it's on the right. It's something that's negative. It's already got extra electrons on it. You don't want to add more electrons to make it neutral. You want to get rid of the electrons. So you have to put the electrons on the right. Okay. If it's a negative ion, the electrons go on the right. If it's a positive ion, the electrons go on the left. Let's try this for the second one. So we've done the half equation for chlorine. Let's try it for sodium now. I'm going to follow the same steps in ion babe. So we're going to start off with the ions on the left. So sodium on the left, Na+. Next, we have the atom. Is sodium diatomic? Is it a gin? You can do it with a minus. You can't. You won't get marks if you write it with a minus. It's a good idea. The other exam boards accept it. I think OCR accepts it, but AQA doesn't. No, it's not. It's not diatomic. There's nothing to do there. So does that mean we need to balance atoms? No, we don't. The atoms are already balanced. So we go straight into balancing electrons now. So add electrons to the left. We only need to add 1 electron here. And we're good. That's it. Those are the 2 half equations. If you're IGCSE, then yeah, maybe you might need to. Okay, so that's what all of this goes through. It goes through those steps, guys. So here we go. All the gens here, diatomic, and it walks through the steps. So you guys can try those out. There's a specific example you guys need to know, which is electrolysis for extracting aluminium. So remember I said that if a metal is more reactive than carbon, then it needs electrolysis to extract. Aluminium is one of them, and this is the one that you need to specifically know. So in order to do this, you need to get the aluminium ore, which is basically aluminium oxide, and you need to use electrolysis to basically split up the aluminium and the oxygen. All right. The problem with this is that aluminium oxide has a very, very high melting point. So in order to make this cheaper, easier to melt, we mix it with another substance called cryolite. Cryolite lowers the melting point of aluminium oxide. It makes it easier to melt, meaning we don't need as much energy. It's much cheaper for us to melt, and we can put it into the electrolyte. So we have our electrolyte here. And just notice this is slightly different, the setup. This is one that they have given in a past exam before, the setup for aluminium oxide. Don't get confused by this. All of these are anodes. The cathode is actually at the edge. It's like lining the container. It's just the way it is, okay? You don't need to know why. It's just the way it is. So what you have in this is aluminium oxide. You have aluminium ions, you have oxygen ions floating around. Remember what's going to happen. You're going to turn the electricity on. The aluminium ions are going to go to the negative cathode, and the O2 minuses are going to go to the positive anodes. And it's going to look like this. So if we do I am babe again, these are the half equations you're going to get. Al, it's not diatomic. We don't need to balance it. We add electrons. We have to add 3 electrons because aluminium is 3 plus. Oxygen, we do the same. And the final half equation looks like that. Okay. Some of it have a hole at the bottom to let the aluminium out. Yep, because the aluminium gets produced. Exactly. So once this happens, you get aluminium being produced here. And remember, this is molten. So it's very high temperatures. So what happens is that aluminium trickles to the bottom and you can collect it. Sometimes it has a hole. You can collect it. Oxygen gets produced here. Oxygen gas gets produced. So you get bubbles. You get bubbles of oxygen here. And you get molten aluminium here, which we can collect. A problem that we get is that this oxygen can react with the electrodes. Do you guys know what the electrodes are made out of? It's one of the allotropes of carbon. What's it made out of? It is made out of graphite. Yes, Dennis, well done. So that carbon can react with oxygen. Remember, graphite is made out of carbon. It can react with the oxygen to form carbon dioxide. And that is a problem because it's going to wear away all the carbon in these electrodes. And it's going to get smaller and smaller. So you need to constantly replace these electrodes. Well done, guys. Right, last stretch, nearly done. Electrolysis of aqueous solutions. Remember, everything we've talked about up to now is to do with molten electrolytes. We're going to talk about aqueous electrolytes now. Aqueous means dissolved in water, meaning it has water in it. So as well as whatever the ionic compound has, the water also forms ions. Water can ionize as well. It forms H plus ions and OH minus ions. So the example we did before was molten sodium chloride. Now let's look at aqueous sodium chloride. Aqueous sodium chloride, just like before, has sodium ions, chloride ions, but on top of that, it also has H plus ions and OH minus ions because that comes from the water. None of this would be present if it was molten. That's why molten is so easy. You can predict what's going to get formed. But for aqueous ones, you can't predict. You don't know. It could be hydrogen that gets formed. It could be sodium. It could be oxygen that gets formed. It could be chlorine. You have to be able to predict it because it's a mess inside the electrolyte. Look at this. We've got sodium ions, chloride ions, but we also have OH minus ions and H plus ions as well. We need to decide which ones are going to go to the electrodes. Where's the diagram? Do we have a diagram here? Yeah, we need to decide which one's going to go. Now, there's only one that can go. So remember I said a positive one needs to go to the negative electrode. So is it the H plus that goes to the anode, the cathode, sorry, or is it the Na plus? How do we decide which one it is? Is it H plus or Na plus? What do you guys think? And then for the negative one, is it the chloride that goes, or is it the OH minus ion that goes? This is something that you need to be able to figure out. There we go. GCSE study accounts have got it. So basically, you decide based on the reactivity. So out of these two positive ions, you have to see which one's least reactive. Do you remember when I showed you the reactivity series? Hydrogen is lower than sodium. Whichever one's less reactive, that's the one that's going to go to the cathode and form whatever element is. So what we're going to get here is hydrogen being formed. When it was molten sodium chloride, it was sodium that's being formed at the negative electrode, if you guys remember. But now because it's aqueous, we're getting hydrogen form, hydrogen gas. That's the rule for positive ions. For negative ions, the rule is slightly different. What do you guys think is going to go? The chloride or the hydroxide? How? Yes. There we go. Athena's got it. Cl minus. Yes, chloride goes. The reason why is because it's a halogen. So the rule for negative ions, it's not about reactivity, it's about whether a halogen is present or not. If a halogen is present, the halogen is going to get formed. So chlorine is going to get formed. If halogen is not present, if this was something else, if this was, I don't know, sulfur, then the hydroxide would go and it'll form oxygen. So these are the rules. At the cathode, the less reactive element is produced, so the hydrogen. At the anode, the halogen is produced if a halogen is present. If not, oxygen is produced because the OH minus will go. If the OH minus does go, guys, this is the one half equation you need to memorize. All the other ones you can figure out using IM-BAE, but you can't figure out this one. This one you need to memorize. The half equation for OH minus. So, like I said, hydrogen is less reactive. So hydrogen is the one that's formed. And then here, we used IM-BAE here to work out the half equation, like I showed you earlier. And here, halogen is present. So chlorine is going to be produced. So we write a half equation for chlorine. If you guys want to practice that, got loads more you guys can try out. So what I'd say is basically cover up all of this and then try and figure out from sodium chloride, aqueous sodium chloride, figure out what's produced at the cathode, write an equation for it, what's produced at the anode as well. Got loads for you guys to try out and practice with. What is the point if water compounds are the ones coming out? Basically, you'd rather use aqueous electrolytes because it uses less energy. Like imagine sodium chloride. To turn that molten, you need a really high temperature. You need like 700 degrees. But sodium chloride just dissolves in water. So you could just dissolve it in water and electrolyze it. If you want the element that is not a halogen, you would likely use electrolysis with a molten solution. Yeah, you could just use another. You could just use another compound. Okay, so there's a required practical for electrolysis, but that's basically everything that I've covered. You might see a setup like this, so just be aware of this setup. And also, they could ask you for gas tests as well. These are more paper 2, but if you want to test for chlorine, damp blue litmus bleaches white. Oxygen, add a glowing splint, it should relight. And hydrogen, add a lit splint, and you should hear a squeaky pop. All right. So, guys, we've reached the end of the combined stuff. Okay. We're about to spin the wheel. I just want to quickly go through fuel cells for triple. That'll be very quick. And then we'll spin the wheel and we'll say our bye-byes, unless you guys are going now. So really quickly for fuel cells, not much to know. Fuel cells are basically the opposite of electrolysis. You're basically trying to generate electricity by using different electrodes. So these electrodes are not made out of graphite, they're made out of different metals. All right. And those different metals react with your electrolyte and produce a current. And you can work out the potential difference of that current. All right. So remember, this is triple only, guys. I'll be like 5 minutes, 5 minutes. So the difference between it, electrolysis uses electricity, and it produces a chemical reaction. Fuel cells do the opposite. They use a chemical reaction and they produce electricity. And the way they work, like I said, is you get two electrodes with different metals. You put them in a solution and it produces electricity, a potential difference. The bigger the potential difference, the bigger the voltage, the bigger the difference in reactivity. So if we look at this, copper and cobalt have a big voltage, but copper and magnesium have an even bigger voltage, plus 2.71. So that means magnesium and copper have the biggest difference in reactivity. And you can assume that magnesium is the most reactive here because the voltage is the biggest. Silver is the least reactive because it's minus 0.46. So you can basically predict how reactive a metal is by using that. Batteries are loads of these cells. So we call this a cell. Loads of these cells connected in series. So you basically put loads of these in series to create a much bigger voltage. That's how batteries work, basically. So non-rechargeable one, it has a reaction, and once the reactants are used up, that's it, it's finished. If it's a rechargeable battery, you can reverse the reaction because it's a reversible reaction, and you can start the whole process again. You just need to pass electricity through it. And then finally, we've got fuel cells. Fuel cells are special cells that produce electricity by you pumping fuel into it. So they work like chemical cells, but you're pumping fuel. So the most common one that comes up in exams is a hydrogen fuel cell. So in a hydrogen fuel cell, you've basically got an anode and a cathode. At the anode, hydrogen is oxidized. At the cathode, oxygen is reduced. So these are the reactions that happen. So the overall reaction, hydrogen is reacting with with oxygen to form water. That process releases energy, which we use to create electricity. So you need to know the overall equation here and the two half equations. You need to memorize those equations as well. So the good thing about hydrogen fuel cells, as opposed to using batteries, is they don't use toxic chemicals. They don't release toxic chemicals when you throw them away. They're faster to refuel. A battery, you need to stick into a socket and let it charge up. Whereas a fuel cell, you just need to add more fuel and it will create electricity. Disadvantages is that hydrogen fuel cells, they do use fossil fuels. We get hydrogen from fossil fuels, and fossil fuels are non-renewable. Hydrogen is explosive and it's very difficult to store as well. That's all. That's all it is, guys. That is all it is. Wow, wow, wow. Well done to the 56 of you who lasted to the end. Well done. That was a lot of content. But remember, you guys can always go back and revisit it all. I'm knackered. I don't know about you guys. I've done a lot of talking. My throat's hurting, but at least there's that Easter weekend coming up. Whew. Let's spin the wheel then. I know that's what you guys are waiting for. No worries, guys. Thanks. Thank you all for your kind comments. I know I know people were losing concentration in it. I know how it is. But I'm hoping this helps you guys out for your exams. So this is our last one, the last paper one boot camp before next week. We've got our paper 2. So remember, guys, we've got limited spaces in the paper 2 ones. If you're part of FRL classes, don't worry, you're automatically in that. And yeah, after this, you guys can sign up if you want a space there. You guys know now what you're going to get. It's going to be high intensity. It's going to be from 10 a.m. to 3:30 p.m. It's the same thing, but it's just paper 2 content. So if you guys like what we've been doing here and you want to join the paper 2s, then come and join. The more the merrier. I feel like we've built like a community here. Everyone, I'm seeing like a familiar face, familiar names here as well. So it's good to see. If I don't see you guys again, good luck. I might see you at the cram class. Good luck with your revision. Keep pushing. And yeah, not long left. Next month is literally the exams. And if I do see you, I'll see you next week. Right. Are we ready to spin the wheel? Are we ready? Ready? And then you guys can ask me any extra questions. Let me get it up on the screen first. Okay. We have several names here. Drum roll, drum roll. Let's see who's going to land on. Let's go. Who's the winner? We've got Harish. Well done. Is that the same Harish that's in my tutoring class? If it is, well done. Is it actually him, Akshon? He was saying he was so close last time and he wanted to get it. He got it. He got it. Well done. Smashed it. Congratulations. Maybe you can drop a message in the chat now. Panir says rigged. Oh. Anyway, guys, that was good. Let me know if you have any any questions in the chat, and I can answer them. So any questions on chemistry, last minute questions, I'll stay behind and answer it. Could we do a revise for a prize on Sunday? Let's see. Actually, no, because it's bank holiday this week, so I probably won't do it this week. When we come back from Easter, then I'll do a few. How can we join the cram lessons? I'll drop a link in a second. Let me drop it in right now. For the cram classes, the link. So yeah, like I said, the paper 1s are free, and the paper 2s are £10 each, guys. So it's like $2.50 an hour. Okay, so no questions on chemistry. You guys done? You're tapped out. No worries if there's no questions. Year 10, yeah. So if you're year 10, then we will. Well, I'll have to think about it. Maybe over summer we'll have stuff to get you guys ready for year 11. Just yeah, we'll email you. If you've signed up to the cram class as a year 10, then we can send you guys like any information on what we'll be doing. Okay, let's see some of these questions. Do we need to know which elements that was there and which was left for the history of the periodic table? No, you don't need to memorize any of those elements. Good question. Is that the same paper 2 class? Was already signed up for that? No, Coral, it's different. Cram classes are different to paper 2 classes. The cram classes are classes that we're holding the day before each of your papers. So that's separate. Will the plus and the minus have an effect on the voltage? Yes. More negative it is, the less reactive it is. No, we can't do another one. Sorry. Let me see what we have. On your website, do the FRR trio class have 3 live lessons a week? Yeah, so if you are part of the trio classes, you have access to all the live classes, the cram classes and the paper 2 classes, all of that for £22. And yeah, we've got extra FRR classes as soon as this Easter's finished. So you'll get 3 classes a week on Friday and 2 on Sundays as well. How to structure and evaluate question. Write about both sides of the argument. Okay, so advantages and disadvantages, and always add a conclusion at the end. A lot of the times, it doesn't matter what you write as the conclusion. You'll still get the marks. What were the differences between modern and Mendeleev's periodic table? Mendeleev left a lot of gaps. The modern periodic table doesn't have any gaps in it. It's the one that you have at the back of your exam, so it doesn't have any gaps. There've been 3 lessons have been spectacular. Great to hear. I hope I see you in the paper 2s. If not, good luck. How do you sign up to the Kahoots? Just turn up. I'm not sure when the next one will be. It'll probably be the Wednesday after school starts again. What did I get? GCSE Chem, A-star. Who won the wheels? Harish. Can I go from a 4 to a 9 in Chem? 4 to a 9? Possible. I've seen someone go from a 5 to a 9 before. I've never seen someone go from 4 to a 9, but you can definitely raise it up by 4 marks, by 4 grades, sorry. You still have time. You still have another week of Easter. It's possible. Just try your best. Try and revise as hard as you can, and try and do as many past papers as you can as well. No, paper 2 will send out links. It's different. What do I get you? What's the difference between? Sorry, I'm seeing all these messages. I'm trying to get them. Do we need to know the transformation of the periodic table? Transformation. You need to know mainly about everything that's in the revision guide, the early periodic tables and Mendeleev's periodic tables, and how it led to it. You don't need to know. You need to know those 2 points that I said about the gaps and the fact that he switched orders around. Switched the orders of elements around as well. Can we get the edited guide? Okay, Coral, I'll try and send that out to you guys. We'll be sending out the mark schemes to the questions on it as well. If you have 5 weeks left before exams, how to revise properly. Go through the notes. You still have time, okay? Until the end of Easter, I keep telling people you still have time to smash it out and to get your grades up. Yeah, you think about this. You have a full day. Look, what did we do today? We went through the whole syllabus in a day, right? So it's possible for you guys to learn everything, to learn it all. You just need to focus and spend the correct amount of time. So look at the notes, try questions on each topic separately, and then once you've done all of that, try exam questions. Difference between describe and explain questions. Very good question there. Describe means literally say what you see. So in a graph, if it says describe the graph, you say it goes up and it levels off. You don't need to say why. If it says explain, you have to say why is it rising? Why is it leveling off? You have to explain it. You have to give more context to it. Deborah, no worries. Hope I see you at the paper 2s. Year 10 summer session. If there's enough, what's the word I'm looking for? If enough people want it, basically, I'll do a year 10 summer session. Yeah, that sounds good. How can you access the mark scheme? We'll send that round to you. See you in the cram classes. Yes, Seth, I'll see you then. No worries, no worries. Can we use the RA number that they give you? What RA number are you talking about? Sorry, who said that? That was Coral. RA number that they give you to find proton and electron number. What do you mean by RA number? Best thing to do now is exam practice, only if you know your stuff. So go through the spec points, Crispy, and tick off what you know and what you don't know, revisit it. After you're quite confident with the content, then do exam practice. Paper 2, yeah, there's more stuff. It's going to be more in depth. It's harder topics as well. Recommendations for paper 2. We have a lot of free resources, guys. Go on our website. We've got the notes. Go through the notes and try the exam questions if you can't make the boot camp. Should we be revising certain topics more than others? Yes. Do the ones that come up more and the ones that you find hard more. If you're just doing loads of easy questions, then you're not really improving your skills. So you need to try a bit of everything. Loads of people like avoid 6 markers. So definitely go and practice those. Yeah, I'll send out the edited guides. I'll try and send that out. Is there a list for more common important topics? Oof, that's a tricky one. The required practicals for biology, photosynthesis and respiration. Chemistry. What always comes up? It's hard for me to say. It's hard for me to say. But if you go through a few past papers, you'll be able to see like what comes up more. Is hydrogen make covalent bond or ionic? It can make both. If it's a H+, it can make ionic. Otherwise, it can make covalent bonds. Any predictions? No, sorry, I don't make predictions. They're not accurate. Sometimes, if you're lucky, they are. If not, they're not. For explained, you have to describe it as well. Just to be safe, I would describe it because you're basically saying it increases because. So you are kind of describing it when you're explaining it. What's the easiest paper in your opinion? Bio paper 1 out of all of the sciences. Yes and no. It'll be more exam focused. 9. What's the best way to improve in chem? Notes, questions, notes and questions. So go through the notes, try questions topic by topic, one by one. No predictions. Sorry, guys, I don't do any predictions. In the periodic table, because they give you a whole number by a decimal point. Use what's in the periodic table if you're not sure. In your periodic table, don't use any ones with decimals. Only chlorine has decimals, and one more, I think, has a decimal. You're here on your birthday. Well, happy birthday to you. That's good. You're revising on your birthday. Nice. I'm not sure, Dennis. I never saw the paper. I never saw the 2025 paper. So apparently it was accurate, but I'm not sure. Thank you so much for the genuine help. Thank you so much for that message, Safa. That's really good to hear. Thank you for that. Why did Mendeleev's table get accepted? Because he made these gaps and he said he predicted the properties of those elements and it turned out to be right. So people accepted it. We'll send the mark schemes. Yes, as I said before. Did you create paper 2 cheat sheet? Yes, we created paper 2 cheat sheets. So that's for people who sign up for the second cram class. They'll get that sent to them as well. You're going to go back to electrolysis because you missed it. Okay, hope it goes well. Good luck. Hardest paper. Ooh. Chemistry paper 1, maybe. Chemistry paper 1. I think chemistry paper 1 is harder than chemistry paper 2. Which topic to revise the most? Electrolysis, I would say, because it comes up a lot. It's a required practical and it's the hardest. How many hours of science revision should we do? It depends. It depends on you. It depends on how much you want to improve by in science, how good you are at the other topics. Are you going to do science at A level? I told all my students, try and do 4 hours a day during this Easter. But yeah, break that up into what you need to prioritize, right? There's maths, English is important as well. Whew. All right, guys. Wow, that was a long one, but I hope to see you guys next week for the paper 2s. So big break now. We've got our website. I've got a TikTok with videos that I'm going to be posting on. We've got YouTube, which we're going to be posting on, and we've also got the paper 2 sessions. So yeah, thank you so much, guys. I will see you all when I see you. All right, guys. Sorry I didn't answer some of these questions. On which topic are we? Which topic to revise most for? Biology, photosynthesis, and respiration. How many hours? Honestly, I can't tell you. It depends on the person. It depends on the person. You'll get your mark schemes eventually. Don't worry, guys. And if you have any questions, also, guys, you can email us help@flashrevisionlab.com. So if you do have any, do let us know. All right, guys. Good luck, everyone. And I'll see you soon. Bye.